Hello, everyone. This is the combined lecture for Physics 102, both March 25th and March 27th, and for Physics 112, March 26th. Okay, so today's lecture is actually going to be on thermodynamics. We'll complete the entire topic today. And let's begin by logging into our Moodle site, and I'll show you where the notes are. Okay, so go to our Moodle site. It's the usual username, password, and let me show you first in Physics 102 here. Under Physics 102, scroll all the way to the bottom there, and there's the March 25th, 27th notes. All right, or if you're in Physics 112, the notes are here, March 26th, and they're both identical. I should just say that um, for some of these lectures I can combine them, but for other lectures I will not be able to combine them because basically Physics 102 is Physics 111, but it has calculus and a lot more math in it. And when I have to diverge between the two, I'll just create a separate video for both of you. Okay. Well, let's begin. And I can see I'm covering up my own writing a little bit here. So let me start off. So thermodynamics is the study of heat. Okay, it's the science of heat, and it was actually Einstein's favorite subject. He said there was no subject more complete, no physics more complete than the study of heat. And so, well, let's begin. The first question is, what is temperature? Okay, so physics is at least since Galileo, physics is all about measuring things, and we really need instruments to measure things. I mean, there was physics before Galileo, but it was qualitative physics. It wasn't very precise. But after Galileo, we strive to create instruments to measure whatever physical phenomena we encounter in the world. And you know that there's such a thing as hot and cold. The same object could be hot sometimes, it could be cold sometimes. And so you're wondering, what is this thing? What is this phenomenon which is hot and cold? Is it like a color? Is it like some fluid inside of the material? These sorts of theories were being bounced around. But by the end of this lecture, uh, we'll understand what temperature is. Okay, so let's begin though by creating an instrument to measure temperature. And you say, well, what do you measure temperature with? And the answer is obvious: it's a thermometer. Okay, so you take a thermometer and you put it in a cold area, and the thermometer is made out of some material, and the material will actually shrink. Okay, in the colder temperature. You take that same thermometer and you put it in a warmer area, and it'll expand. And so you go, aha, there's a clue as to what temperature is. And even if you don't fully understand what's causing the shrinking and the expanding, we will later on. But if you don't understand that, at least you've got some sort of a handle in on the problem, and you can start to design an instrument around that. And so we'll do that. We'll actually create a thermometer. And so the way you have to create a thermometer is basically, down a bit. Basically, what you do is you take some material, and you take that material and you put it into one particular reference temperature, and you measure the length of the material. Now, the material could be, like mercury inside of a glass tube. It could be alcohol inside of a glass tube. Those thermometers that have a red fluid inside of them. That's alcohol with like a little bit of food coloring in it, so you could see it. But it could even be a metal bar. It could be anything because most materials expand and contract in hot and cold areas. Okay, so you take this thermometer and you this bar, say a metal bar, and we put it into one reference temperature, and it shrinks, and we measure its length, and we put it into a hotter area, and it expands, and we measure its length. Okay. Now, the first thing is what two temperatures are you going to choose? Because we're really calibrating. This is kind of like in the lab when you go to measure the mass of something. You have to make sure that your balance, when it doesn't have anything on it, is reading 0 grams, and so you have to calibrate it. So this is the equivalent of calibrating your thermometer. But to calibrate the thermometer, you actually need two different temperatures. Okay, and so where are you going to pick these reference temperatures? And it just turns out that things like phase transitions, which we'll talk about a little later, phase transitions form excellent reference temperatures. For instance, water freezes at a given temperature. Okay, now what you want to call that temperature, that's up to you. You can call it 0 degrees Celsius, the way Celsius did. You can call it 32 degrees Fahrenheit, the way Fahrenheit did. But you can call it any number you like. Okay, but there you go. That's one reference temperature, and water always freezes at that temperature. Okay, and you can easily do that experiment because you can have two pools of water, and you'll discover that they both start to freeze at the same temperature. Okay, or they'll both start to melt at the same temperature. And another reference temperature is boiling. Okay, so when water boils, it always boils at 100 degrees Celsius or 212 degrees Fahrenheit or whatever you like. And so you've got these two reference temperatures, and you measure the bar in frozen water. I guess not really frozen water, but ice water. Okay, because you're guaranteed with ice water that you're at 0 degrees Celsius. Water and ice are in equilibrium at 0 degrees Celsius. And then you put it in boiling water, and water boils always at 100 degrees Celsius. And great, you've got these two lengths. Okay, and so what you're seeing there is my thermometer at the two reference temperatures. So the original length of the thermometer, we'll call that L naught, okay? And the little naught usually means initials, so that's the original, and that's going to be at a temperature T naught, all right? And then, you know, at the higher temperature T, the thermometer has expanded a distance delta L, and you can see that in the diagram there. Okay, so now how does this all, how do these quantities fit together? And it's basically this equation here. This is what you might call a thermometer equation. And the thermometer equation says that your delta L, the amount of expansion that you get, is going to depend on your delta T. So you see delta L on one side and delta T on the other side, and they're linearly related to one another. But there's a couple of other things in there. There's the L naught, which is the original length, and you have to have that in there because the amount of expansion you get will be twice as much if your bar is twice as much, okay, because there's more of the bar to expand. We actually even saw that when we looked at elastic moduli and so on, okay. If there's more material, if the length of material is longer, there's more of it to stretch, it's easier to stretch. In this case, if there's more of the material, then it's more of it will expand, and so the delta L will increase linearly with the original length. But then there's also this alpha in there, and you wonder, what is this alpha? Well, alpha is the coefficient of thermal conductivity, and of linear, sorry, a linear thermal expansion. I apologize. It's the coefficient of linear thermal expansion, and it's basically just a property of the material. And so you could say, you know, for bronze, it has a particular value. For alcohol, it has a particular value, and so on. Okay, it's the value of whatever you're making that thermometer out of. Okay, and so there you go. There's that equation. We're going to use it in a minute to create a thermometer out of alcohol. And there's one assumption, though, in this, and it's actually an incorrect assumption. And the assumption is that delta L and delta T are going to be linear in one another. It's almost true. It's true if delta T is very small. But as your temperature range gets bigger and bigger and bigger, this equation falls apart. And that leads to a problem with thermometers, which we'll talk about in a minute. But let's first do a problem with this. The next thing is what are the units of alpha? Well, the units of delta L and L are obviously meters, and the units of delta T are degrees Celsius or degrees Kelvin. We'll work with both, or it could even be degrees Fahrenheit, but we won't work with Fahrenheit in this course. And so if you work out what the units of alpha are, it just turns out to be per degree Celsius. And you mean, what do you mean per degree Celsius? Well, it's kind of like that delta L over L naught. You can see it right here. Okay, that delta L over L naught. That is basically just a ratio, like how much did it expand per unit length. And of course, that's meter per meter. And so the per Celsius means like what percentage did it expand per degree Celsius, something like that. Okay, so great. It's a really easy formula to use, and so let's go ahead and use that to do some calculations. So it turns out that a metal bar, I said alcohol a minute ago, but we're going to use the reference temperatures of ethanol actually, and we're going to use some metal. I don't know what this metal is, some fictitious metal, but we take this metal bar and we discover that it has a length of 2.35 meters at a temperature at which alcohol freezes. Okay, and it has a length of 2.73 meters at a temperature at which ethanol boils. All right, now at this point we could have chosen our own scale, and I'll show you that below, but let's use the Celsius scale. Okay, and in the Celsius scale, because that's already been pre-established, in the Celsius scale it turns out that alcohol freezes at minus 114 degrees Celsius, which is really cold. Okay, and it boils at 78 degrees Celsius. All right, so there's quite a range there. Okay, so what do I ask you to do here? Well, we're going to use that formula, and we're going to first find alpha. And then we're going to use, once we find alpha, then we can use that formula as we can use the formula with the metal bar to measure temperatures. In other words, it's become a thermometer at that point. So if the bar has a length of 2.49 meters, so that's more than the 2.35 but less than the 2.73. So if it has a length of 2.49 meters, what's the temperature? Okay, so you can see there it's acting like a thermometer, because in a thermometer the length through that formula gets mapped to a temperature. Okay, but it's the other way around too. You could say, look, the temperature is 0 degrees Celsius. What length do I expect for this bar? Okay, so using our thermometer formula, I first rearranged it. Okay, and so basically I just isolated alpha on the one side here, and so there you could see the delta L over L naught, and this is delta T, but to the -1. It's actually in the denominator. Okay, and so we take the delta L. This is the L from the where ethanol freezes to the point where ethanol boils. Okay, we take that length change, and it turns out that that length change is 0.38 meters. Okay, and what's the delta T? All right, well, the delta T is a higher temperature, 78 degrees, minus the minus 114, which means that delta T, that is the temperature from when it freezes to when it boils, that range is 192 degrees Celsius. So this is actually quite a big range. Okay. All right. Once we have that, we plug in. And also we need the L naught, which is the original length of the bar. That's the length of the bar at the lower temperature. Okay. So we take the original length of the bar, 0.235, and plug that into the formula, and you will get this number 0.000842 per degree Celsius. Okay, or there it is written in scientific notation, 8.42 times 10 to the -4 per degree Celsius. All right, great. Now what? Well, we answered part A. We've got alpha. So actually we have everything we need to go ahead and use this bar as a thermometer. So now we have some region of unknown temperature, and what we do is we take the bar and we put this bar into a region of this unknown temperature, and of course it adjusts its length until it finally reaches 2.49 meters. Okay, and we ask, what's the temperature of that region? Okay, so delta L is going to be the 2.49 minus the 2.35. That's how much it expanded above the lower reference temperature. So the lower reference temperature where ethanol freezes, that's going to be like where our L naught is, and we measure the delta L relative to L naught. Just take a look at that diagram above to remind yourself, okay? And so it turns out that the bar expanded a length of 0.14 meters over the lower temperature, okay? And now if we plug that delta L in to our equation, and here all I did was I took the equation above and I rearranged it so that delta T is isolated on the left hand side. So I have delta L over L naught, but also over alpha, and we plug in our numbers. Delta L we just determined was 0.14 meters. Alpha we determined in part A was that 8.42 times 10 to the -4. Also, L naught is 2.35. We work that out, and ta-da, we get 70.7 degrees Celsius. But we have to be careful here, and this is a common mistake that the students make with this problem. Okay, that's not T. Whoops. I just lost the capture. This happens every once in a while. There we go. So that's not T. That's delta T. What does that mean that it's delta T? It means it's 70.7 degrees Celsius above the lower reference temperature, okay? Because everything's being measured relative to that lower reference temperature. Now the lower reference temperature was minus 114 degrees Celsius, so you're 70 degrees above that. So what does that mean? Well, I mean, you could just use the formula directly for it. Delta T is your actual temperature minus T naught. The delta T we found to be 70.7. That's equal to the temperature that you want to find minus the minus 114. And so you work that through, and it turns out to be that the temperature in that particular region is minus 43.3 degrees Celsius. Okay, so just be careful about that, because the formula works in delta L's and delta T's. It doesn't work in L's and T's directly, okay? And so when you get a delta T, that's a delta T above the lower reference temperature, and that's a delta L over the L naught, okay? And so just, if you're careful with that, then you'll be fine. So now let's turn that around, okay? suppose that I know the temperature, and I might know that temperature for other reasons. For instance, I know it's 0 degrees Celsius because that's the temperature at which water freezes, okay? And so you say, okay, I'm going to put my bar into this region of space where I know the temperature is 0 degrees Celsius. How long do I expect the bar to be? And, well, there it is, okay? So we take delta L is equal to alpha L naught delta T, and we don't have to even rearrange it because we're solving for delta L. And so we substitute in all of our numbers. We substitute in for alpha that we found above, the L naught 2.35 throughout the problem. And now delta T is, you're at a temperature 0, and that's above that minus 114, so it's 0 minus 114. Notice the double minus in there because you're subtracting the second temperature. You're subtracting the T naught, but the T naught itself is negative, so it's 0 minus 114, and you just work that through on your calculator and you'll get 0.226 meters, okay? Again, that is not the length of the bar. That's how much the bar expanded. That's your delta L. That's how much the bar expanded over the reference length of 2.35. Okay, so just like the story with the delta T, we have the same situation here. And so I note that very carefully. So we have that delta L is L minus L naught. So that's 0.226 is equal to L minus 2.35. Okay, and basically that gives us our answer that the bar would have a length of 2.576 meters. Okay, and so that answers the problem. Now, I want to show you how this could actually be used to make a thermometer. Even if you don't have a temperature scale already. Okay, so here we pretended that we already had a temperature scale. Okay, and we used it. All right, which is fine. But pretend that you're making a thermometer for the very, very first time. Okay, and that's exactly what Celsius did. And so what he did was instead of using ethanol, he used water. Okay, and so he said, okay, I know a good reference temperature for water. It's the temperature at which water begins to freeze, 0 degrees Celsius. And I know another good reference temperature for water. That's the temperature at which water boils, 100 degrees Celsius. And he arbitrarily called them 0 and 100. He could have called them something else, but he chose 0 and 100 because that makes sense. It's a nice 100 is a nice even number. And we got the Celsius scale. In the Celsius scale, water freezes at 0 degrees Celsius. Room temperature is 20 degrees Celsius. Water boils at 100 degrees Celsius. A hot day is 30 degrees Celsius. A super hot day, like bordering on desert, would be maybe 40 degrees Celsius, something like that. Okay, but like if we had never seen any temperature scale before, I could have just as well said, you know what, I'm going to make this new temperature scale. I'm going to call it A. A for alcohol, maybe. And so we're going to say, you know what? Yeah, when ethanol freezes at minus 114 degrees Celsius, but I don't know that. I'm just going to call the temperature at which ethanol freezes 0 degrees A. And I'm going to say the temperature at which ethanol boils is 100 degrees A. And then I'm going to use my thermometer formula, and ta-da, I have a brand new temperature scale. Okay, and in fact, this is what Fahrenheit did. Fahrenheit wasn't looking at water freezing and boiling. He was more worried about sea travel, and so he looked at the temperature at which fresh water freezes and the temperature at which salt water freezes, and these two are seawater freezes, and these two temperatures are different temperatures. And so what he said was, I'm going to make the temperature at which seawater freezes 0 and the temperature at which fresh water freezes 32. And that's how he got the Fahrenheit scale. You might wonder, why did he choose 32? Why didn't he choose 100 or some nice even number like that? And the reason he chose 32 is because it's a power 2. Because if you take a length and you want half the length, you just, like you have a piece of paper and you want half of the piece of paper, you just fold it in half. You want a quarter, you fold it in half again. Now you got a quarter and you fold it in half again, an eighth, then a 16th, then 32nd. And that's why we got that water freezes at 32 degrees Celsius. For 32 degrees Fahrenheit. Okay, so you can make up, you can use that formula, and you can make up any temperature scale you like. Okay, great. So we started off the class, this lecture, by saying how do we get a handle on temperature? And the answer was we can just use an instrument, and so now we have a handle on temperature. Okay. Now I told you there was a problem with uh, the scale. Okay, so what is that problem? The problem is that the the assumption underlying everything we've done right now is linearity. Okay, so here, in order to make this temperature scale, we need two reference temperatures. Okay, and so we can have two different materials, say bronze and steel, or alcohol and mercury. Mercury thermometers. We don't make thermometers out of mercury anymore because mercury is a heavy metal. It's a bit dangerous, but you could have different materials, and we can make thermometers that would agree at those two temperatures, because after all, we're calibrating them at those two temperatures. All right, but would they agree at a temperature in the middle? And the answer is no. They would agree at a middle temperature if there really was linear expansion, meaning that delta L really was linear in delta T. Okay, but it doesn't quite work out that way. Most materials have a bit of a curvature to their expansion rate. In other words, they'll expand a little bit slower at first, and then they'll start to expand faster, or the other way around. They'll expand fast at first, and then their expansion will slow down as the temperature increases. And so what happens is, depending on the two materials that you have, they'll begin to disagree at the middle temperatures. Okay, and that's what I'm trying to indicate here with, whoops, move it up a bit more, with this graph. Okay, and so this is just a schematic graph here, but basically I'm just plotting delta L, that's like how much L, how much the length increases as a function of T. Okay, and so we've just got these two materials, all right, and they can be any two materials, and we've calibrated them, we've made them agree, so they both have a delta L of 0 at the lower temperature. Okay, and then at the higher temperature, the higher reference temperature, okay, there's going to be some delta L for each one of them. And in fact, probably to get them to agree, I'd have to normalize them somehow, but I'm not worried about the details. Basically, they're going to agree at the lower temperature. Okay, both thermometers are going to say, yeah, we're at the temperature 0 degrees Celsius. Okay, because you made it, you designed the thermometer that way, and they'll agree. They'll both be able to predict and agree that, water is boiling. So they're your two reference temperatures. But in the middle, at some intermediate temperature, because material 2 is expanding with a positive curvature there, and material 1 is expanding with a negative curvature, in the middle, they disagree. And so one thermometer will say, oh, it's one temperature, and another thermometer will say it's another temperature, and you'll go, well, which temperature is it? Okay, like you can't decide that one is true and the other one's false. Like you have no basis of deciding which one is the correct thermometer and which one isn't. And in fact, neither of them are right. Okay, because both of them are deviating from that linear behavior, that linearity between delta L and delta T that was assumed above. Okay, and so we're kind of stuck, because yeah, we've got a handle on what temperature is. It's got something to do with causing things to expand, but we really can't work on it. I mean, the equivalent of this is if we were talking about time, we might have different clocks. And our clocks would agree that it's midnight, but then during the day, one clock was running faster and then slows down. Another clock runs fast at first and then speeds slow at first and then speeds up. And so the clocks in the middle of the day, they disagree, but then they're forced to agree at night. Okay, I'd say at midnight. And you go, well, what time is it? Like if you've got all your clocks at different times, you don't know what's going on. Okay, it's not that big of an effect, but it's there. Okay, it's definitely measurable, and so you really don't fully understand what temperature is. You just know that it's got something to do with causing materials to expand. Okay, so um, uh, well, I was going to say go on to ideal gases, but before I do, actually, there's one material where this effect is absolutely dramatic, and that is water. Okay, you really can't make thermometer out of water, and the reason is that water has this very interesting property that it's densest at uh, um, 4 degrees Celsius. Okay, so what that means is, suppose you have like some volume of water. I tried to draw it in this graph here. Okay, suppose you've got some volume of water, and you start up here at a high temperature. Okay, and so there's some higher volume. Okay, as you cool this water down, okay, so you say you're at 8 degrees Celsius. As you cool it down, what happens is the water its volume will decrease, and so even if it's in a thermometer, the length would decrease. Okay, it will decrease until you get to 4 degrees Celsius, and then something very weird happens. It starts to expand again. Okay, so water that's been cooled down below 4 degrees Celsius starts to expand again. And you say, well, what's the problem with that? Well, the problem with that is you're trying to make, a thermometer onto this. And so you want to put little tick marks. You know, if the thermometer is this length, it's a certain temperature. If it's that length, it's a certain temperature. So that length, it's a certain temperature. Well, if you find the minimum length, you know that's 4 degrees Celsius. But what if you're longer? Are you above 4 degrees or are you below 4 degrees? And so that's what I'm trying to show here. Suppose you know the volume of this water, this column of water is like V naught. Okay? And you just try to read off of this graph. You could be at a temperature which is below 4 degrees Celsius, but you could also be at a temperature which is above 4 degrees Celsius. So this is like the worst possible case scenario for a thermometer, where every single little tick mark would actually correspond to two possible temperatures, a temperature above 4 degrees Celsius and a temperature below 4 degrees Celsius. And so, yeah, this effect can be quite dramatic, in which case you basically just couldn't even use such a thermometer because you wouldn't know. You wouldn't know if the temperature is increasing or decreasing. The best you could do with such a thermometer is say, oh, I'm at 4 degrees Celsius, but you can't do anything else with it. Okay. Now, you might ask, well, why is water so weird? Well, water has this property that when water freezes, it expands, okay? And most materials don't do that. So, for instance, if you had ethanol and you start to freeze the ethanol, it'll just condense into a solid form, and the ethanol ice cubes will actually sink inside of ethanol. They'll be denser than the ethanol liquid, okay? And so, water doesn't do that, though. Water is unusual as a material because it'll expand, okay? And so that's why ice floats on top of water. And, I mean, there's reasons for that because the molecules of water, those V-shaped H2O molecules, they have to kind of start to arrange themselves into a lattice, and that causes the expansion. All right, so yeah, so this is a real effect. Now we can get to the ideal gases. The question is there some material where it is really linear, okay? Or if it's not linear everywhere, it's at least linear over a very, very large range. And the answer is yes, it's ideal gases, okay? Ideal gases act like perfect thermometers. And you go, well, why is that? Why do ideal gases act as like perfect thermometers? I'll kind of get to the microscopic explanation in terms of what the molecules, atoms and molecules are doing later, but they do, okay? Now, what is an ideal gas? An ideal gas is a gas at a very low density. Okay, it has to be a low density because part of the theory about why ideal gases form perfect thermometers is that the atoms and molecules, when they're flying around, they miss one another. Okay, this is a gas, and so the atoms and molecules, whatever the gas is made out of, they're not pushing up against one another like they would in a solid. They're locked into a lattice. In a liquid, they're kind of tumbling over one another, but in a gas, they're just flying free of one another, okay? Now, you can have a situation where they're flying free of one another, but there's enough of them that they tend to collide, and that happens even in our regular atmosphere, okay? There's a certain length that a nitrogen or an oxygen molecule will travel before it encounters another oxygen or nitrogen molecule, all right? But in an ideal gas, we're going to make sure that these atoms, molecules are so far apart that they tend to miss one another. Okay, and then you get into the situation of an ideal gas. All right, and you can do some experiments with these, and I'll kind of describe the experiments below because first I want to get to the ideal gas law itself. Okay, but you can do these experiments, and the experiments are basically you apply a certain amount of pressure to a gas and you keep the pressure the same, all right, and you add heat to the gas, or you take heat away from the gas, and the gas will expand and contract depending on how much, what the temperature of the gas is, and you can plot the volume of the gas versus temperature, and you got to plot something like this, okay? And so what you're seeing here on the vertical slope is the volume of the gas, all right? And what you're seeing here on the horizontal axis, sorry, is the temperature. Okay, so vertical axis volume, horizontal temperature, and over here you can see V is equal to 0. Okay, so that's 0 volume. And you say, well, what does that mean for a gas? I mean, if the gas really were cooled down to that point, it would just have vanishingly small volume. Okay, the volume, like it would just keep, here we are at a temperature, here we are at a colder temperature, colder temperature, colder temperature, and then finally the volume vanishes. Okay, now in reality that doesn't happen. Before you get to where the volume vanishes, what happens is the ideal gas will turn into a non-ideal gas, and then it'll turn into a liquid and a solid and so on. Okay, But you know what? We're not going to push it that far. Let's look at the graph now. So those X's there, they correspond to, say, data points. And we're going to have all bunch of different gases. So we can have helium, we can have neon, we can have oxygen, we can have nitrogen, whatever gases we like, okay? And we have different volumes, or sorry, not different volumes, but different amounts of those gases. We can have lots of helium. We can have very little neon, okay? It really doesn't matter, but we're going to do this experiment where at different temperatures, we're going to measure the volume. And so here for gas 1, we've got a certain temperature, we've got a certain volume. Then we cool it off, and the volume decreases. The volume decreases. The volume decreases, okay, as we cool it. And we just put these data points, and we go, hey, look, those data points, they form a line. So we take this line, and we just extrapolate it all the way down to 0 volume. Okay, again, the real gas can't get there, so the data points can't go all the way down to 0 volume, but they point towards 0 volume because of this extrapolation, and it gets to this temperature that I'm calling in this graph T naught. Okay, then I've got gas 2, and I do the same experiment, and I've got, one data point, another, and I extrapolate down, and ta-da, it gets to this T naught. It actually points to the same one. And gas 3 also points to the same one. And no matter how you do this with these ideal gases, and you just measure their volumes versus temperature, and you extrapolate to 0 volume, you get to a temperature. Okay, one temperature. They all extrapolate to the same temperature. And you might ask yourself, what is this temperature at which all ideal gases have vanishingly small volume? And the answer is absolute 0. Okay, absolute 0. So it's not that they'll actually get there, but they all point to this magical temperature below which there is no other temperature. Okay, so just like your volume shrinks to 0 and that's it, that temperature will go down to this lowest possible temperature, and that's it. Think about it this way: there's no volume less than 0. Once you get to 0 volume, like, can you have a negative volume? Here you can have like a gas in a cylinder with a piston on top, all right? And it'll shrink, it'll shrink, it'll shrink. And it gets to 0 volume. Can it shrink anymore? I mean, I can't even imagine such a thing. And it's the same thing with the temperature. The temperature will go down, 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 and it'll get to a bottom, and that's it. This is the coldest possible temperature there exists. Okay? And this temperature is given the name of absolute 0. All right. Now, we're going to need to use absolute temperature scales later on for when we use PV equals nRT and some of the other formulas, like the Carnot efficiency formula that we'll see towards the end of this lecture. But this absolute 0 is basically the coldest possible temperature. So temperature doesn't just decrease forever; it gets to this bottom, and there it is. It's called absolute 0. Well, above, when we calibrated our thermometers, Celsius did it by saying, okay, 0 degrees Celsius is where water freezes. In our fictitious A scale, 0 degrees A was the temperature with ethanol freezes. Okay, so you know what? How about we create a new scale? And this new scale is going to be is going to have its 0 at absolute 0, and this is known as the Kelvin scale. Okay, so 0 degrees Kelvin corresponds to absolute 0. All right. Now, the next thing is, well, okay, great. The 0 of the Kelvin scale is absolute 0, but how big is a Kelvin degree? Because you can make a big Kelvin degree, you can have a small Kelvin degree, and the answer is we'll make a Kelvin degree the same size as a Celsius degree. All right, there's no reason not to do that. And so if absolute 0 is at minus 273 degrees Celsius, then in the Kelvin scale, water will freeze at 273 degrees Kelvin. Okay, and so here we go. We can actually compare the Kelvin scale, the Celsius scale, and I put in there the Fahrenheit scale just for another comparison to show you. And so we can take a look at 3 reference temperatures now. We can look at absolute 0, and in Celsius, that's minus 273 degrees Celsius. Water freezes at 0 degrees Celsius, and water boils at 100 degrees Celsius. Okay, now if we switch over to the Kelvin scale, absolute 0 is 0 degrees Kelvin. Because a Kelvin degree is the same size as a Celsius degree, water will freeze at 273 Kelvin, and water will boil at 373 degrees Kelvin. In the Fahrenheit scale, water freezes at 32, water boils at 212 Fahrenheit. Okay, and if you just keep going back down, now Fahrenheit degree is smaller than a Celsius degree. So if you just keep extrapolating down, you find that absolute zero in Fahrenheit is minus 460 degrees Fahrenheit. Okay, so there you go. There's temperature scales, and now we know about this absolute zero. All right, and it turns out that because these ideal gases make these perfect thermometers, we were able to measure temperatures over huge ranges, okay, by looking at volume. So we were mapping volume to temperatures instead. Like originally we did length, the length of a column to temperature, but I think you can see that it could be either the length of a column or it could be the volume of the entire gas, okay, that we're mapping to a temperature. And by doing this mapping and just measuring over large temperature scales, we were able to find that there's a bottom to the temperature scale, the coldest possible temperature. There you go. That's absolute zero. All right, so now what? Well, let's turn our attention to the ideal gas law. And we'll actually study it in two forms. Now, I bet you that most of you have seen the ideal gas law in high school or in your chemistry classes and so on. And so usually you see the ideal gas law as PV is equal to nRT. Okay, and I'll explain all of the pieces in there when we get to using this. But there's another form to the ideal gas law, and it's PV is equal to capital N K Boltzmann times T. Okay, and this is a more physics way of writing it, and so, because it actually comes out of Newton's laws. Okay, so yeah, the ideal gas law can be derived from Newton's laws. Okay, so let's take a look at this uh, ideal gas law and how it comes about. I for physics 102, I usually do the derivation. It's pretty easy. For physics 112, I don't. I'm not going to do it this year because of the unusual circumstances. It's not at all difficult, which is remarkable. You can just use Newton's laws, like especially Newton's second law, F equals ma, and you can prove PV equals nRT. And that's kind of a mind blower. You go, well, how do you do that? And the answer's pretty simple. 150 years ago, people weren't sure what gases were made out of. Like they didn't know about atoms and molecules, okay? And I'm going to start calling these things particles, the particles of a gas, because sometimes the particles are atoms, like in the case of helium or neon, or sometimes they're molecules in the case of O2 or N2 or something like that. But they're just basically little particles, like little billiard balls. And what are these little billiard balls doing in the gas? They're just moving, okay? They're just bouncing around, okay? And so because this is an ideal gas, what will happen is the molecules, sorry, the particles, they'll travel in a straight line and they won't hit one another because that's the whole point of an ideal gas. They'll just travel, and the only thing they can hit are the walls of the container. And so you can see here in my diagram, okay? You can see here in my diagram, I've got these little dots. They're the particles. And here's one particle, and we're going to trace its trajectory, and it's just zipping along, and boink, it hits the walls of the container and it bounces. Boink, like that. Now, using conservation of momentum, which is Newton's second law, anyhow, and you just use conservation of momentum. During that collision with the wall, there was a little bit of force between the particle and the wall. Now, the particles are very, very small, but there's a lot of them. And so you basically have this wall, and you've got one particle that comes up and goes boink, and it exerts a little bit of force. And then you got another one boink, and then another one boink, boink. And all these molecules and atoms, they're smacking into the wall over and over and over again. Okay, it's almost like rain. It's just being pummeled by these continuous collisions of these particles, and some of them are coming in steep like that, and some of them are very shallow collisions, and some of them are moving slow and some of them are moving fast. So there's a statistical distribution to the different motions of these particles, okay? And you make use of that statistical distribution. Okay, you make some assumptions like space is the same in all different directions, so there's no one preferred direction over another, and things like that. And you work it through, and this really remarkable equation pops out. It's not quite PV equals nRT. It's this one right here. It's PV, where P is the pressure of the gas, V is the volume of the container, is equal to N, or capital N, where capital N is the number of particles in this gas. Okay, and you literally count them. And you go, well, how can you count all those particles? Well, we don't count each one of them individually, but we have some idea of the number of particles that are in that gas from other means. And then it's multiplied by 2/3 times the average kinetic energy of any one of the particles. And that's the part that's amazing. Okay, now the 2/3, you might go, well, where does that 2/3 come from? Well, the two is big, because of just factors that come out from like 1/2 mv squared being the kinetic energy. But the 3 there is very interesting, because the 3 is the 3 dimensions of space. Okay, and it's part of that isotropy just means that space is the same in all different directions. Okay, there's no preferred direction, and so you actually get a 3 down there. Okay, right there. So but we don't have to worry about that factor. Okay, but I'm just saying, if you're curious, where did it come from? It comes from out of that derivation. But the part that's really interesting is the average kinetic energy. And so basically what you're saying in this ideal gas is that pressure times the volume on the one side is equal to number of particles multiplied by the average kinetic energy of each of the particles. Okay? And you wonder, well, what does this mean? Okay. Now I have a little typo below here, and I apologize for this. I actually get it correct later. Okay. But when you compare PV equals capital N 2/3 KE, when you compare that with this particular formulation of the ideal gas law, the second one, PV is equal to capital N K Boltzmann times T, you discover that kinetic energy in there, that kinetic energy is actually equal to the temperature with some factor in front. Here's where I made my typo, okay? And the typo was I forgot to write in front here. It's 3/2. Don't worry, I get it right later, but I'm just noting this. When you write your notes, note that, correct it, that the average kinetic energy is equal to 3/2 K Boltzmann times T. The 3/2 is just the reciprocal of the 2/3 up here. I don't know why I forgot it, but I did. Okay, but never mind even that K Boltzmann, which is just a constant. Okay, look at what this is saying. This is saying that the average kinetic energy of the particles is equal to the temperature. All right, and so how did we begin this class? I said to you, what is temperature? And, I said to you, well, we need an instrument. Let's at least start to get a handle on this by having some instrument which can measure temperature. And then we found a perfect instrument which could measure temperature with the ideal gas. And then by a theory of how ideal gases work, namely that they're made up of tiny little particles, either atoms or molecules, we found that the temperature is the average kinetic energy of those particles. Okay, so this is rather remarkable. This is remarkable. So when you walk into a cold room and the air is cold, what can you say? You could say that the average kinetic energy of the particles is not that much. And you walk into a hot room and you can say, oh, the average kinetic energy of the particles in this room is hot. Okay, it's faster. They're more energetic. And so the faster these molecules are moving, atoms or molecules are moving, kind of makes sense. The faster they're moving, in other words, the higher the temperature, the harder they hit the wall, and the bigger the pressure is. And so on the one side, you have the average kinetic energy or temperature, because the two are now synonymous to one another. And on the other side, you have the pressure, which is how much force they're exerting per unit area. Okay? The more kinetic energy the particles have, the more oomph they have, the more temperature they have, the more oomph they have, the harder they're going to hit the wall, the higher the pressure for a given volume. All right? And so, when this was done in the mid 1800s, physicists said, yeah, we kind of know what temperature is. It's this average kinetic energy of the particles. And they discovered that through the ideal gas law. Now, they weren't totally certain because, no one had seen an atom or a molecule. That wasn't going to happen for many, many more years into the future. But, the theory works so well. And, in physics, sometimes we do that. We say, geez, this theory works so well. It could be wrong. We need more evidence. But in the meantime, we're just going to use it. And so there it is. Okay. And so if you make use of the fact that the average kinetic energy is equal to the missing 3/2 K Boltzmann times T, and you plug that into the previous formula, you get, ta-da, the ideal gas law. Okay, but the ideal gas law in this second form. All right, so what is it? Now we can look at it. We can look at it in detail. P is the pressure. Okay, and we're going to work in MKS units as we have, and so the pressure is measured in pascals. All right, V is the volume of the container, and also the volume of the gas, because the gas simply fills the entire volume of the container. Okay, it leaves no gaps in there. And so the volume in MKS units is going to be measured in meters cubed. Okay, capital N is literally the number of particles. It's a very large number. It's around 10 to the 23. All right, particles for anything that's macroscopic in size. So if you have, like, I don't know, like this much air, say, like that, in some sphere, roughly 10 to the 23 molecules in there of either nitrogen or oxygen, or there's some argon in air, some carbon dioxide, and so on. But if you were to count them all, you get up to a number which is like a 1 followed by 23 zeros. It's a big number. It's a big number. Okay, and the temperature the temperature in this has to be in this absolute scale, okay? And so we're going to use Kelvin. And the reason is, if you look at the formula again, okay, let's keep a constant pressure. The number of molecules stays the same. K Boltzmann is just a constant. So if we're just looking at varying V and T, when does V become 0? When T becomes 0, okay? So you have to have T here in Kelvin. It won't work. This will not work in Celsius. Imagine that you made this mistake. This would be a very bizarre mistake. Because if you made the mistake and you said, oh, I'm going to plug in 0 degrees Celsius. Well, if you put 0 here, well, then the whole right-hand side is 0. That means the volume is 0. That means that our entire atmosphere would vanish, its volume would vanish at 0 degrees Celsius, which is the temperature at which water freezes. That makes absolutely no sense at all, okay? And so, no. This has to be measured in Kelvin, okay? So it has to be in that absolute scale. All right, so the temperature has to be in Kelvin. And then finally, that leads us to Boltzmann's constant. And Boltzmann's constant is basically just a conversion factor. And what does it do? It converts from whatever your energy units are to whatever your temperature units are. Now, we could have just, measured temperature in joules. All right, it'd be strange. It'd be the equivalent of, like, how many joules on average does every molecule in your gas have? Okay, and there is such a number, but it would be a very strange number. We have this temperature scale. We're not going to throw out the temperature scale just because we've discovered that that temperature is related to the average kinetic energy of the particles, which is measured in joules. And so there's this conversion factor, and the conversion factor is basically Boltzmann's constant, named after a Serbian physicist by the name of Boltzmann that lived about 100 years ago. A brilliant fella who basically gave birth to what today in physics is called statistical mechanics. He made the connection between the microscopic thermodynamics and macroscopic thermodynamics, okay? And it's just a number, and of course I would never ask you to memorize that number on a test. I would just give it to you, and you can see it there on the screen. It's 1.38 times 10 to the minus 3 joules per Kelvin, okay? So there you go. There's the ideal gas law. And you may never have seen it in this form. And so you go, well, I saw it in the other form in my chemistry classes in high school. So how is it that this particular form of the ideal gas law is the same as PV equals nRT? And the answer is, let's define a mole, or Avogadro's number, okay? 1 mole of a substance is basically equal to a certain number of particles, okay? And how that was chosen, I'll let your chemistry teachers tell you that, okay? It's not that important, but we have this mole of substance, and it turns out that 1 mole is the same as 6.02 times 10 to the 3 particles. Okay, so we just define that. Just like we say, a dozen eggs is 12 eggs. So who decided that? Well, I don't know, somewhere in our distant past, in our history, we decided that we would sell eggs in bundles of 12. And whenever you got a bundle of 12 eggs, we call that a dozen. All right, and so if you got 2 dozen, then you had 24, 3 dozen, 36, and so on. Okay, so easy enough. Well, we're just going to bundle a bunch of particles together. If we bundle together 6.02 times 10 to the 23 particles, we say, hey, here's a mole. And we add another 6.02 times 10 to the 23 particles. There you go. There's another mole. Okay, so every mole has that amount of particles. And so you can convert between the two. Now, let's use that in our ideal gas law, the way we have it. So we had PV is equal to NK Boltzmann times T. Let's divide and multiply by Avogadro's number, which is Na. That's that 6.02 times 10 to the 23. So there you can see that I took the capital N and I divided by Avogadro's number. And I also took Avogadro's number and I multiply it by K Boltzmann. And I get that R which is the ideal gas constant, is just going to equal Avogadro's number times K Boltzmann, which is just going to equal in MKS units 8.314 joules per mole Kelvin. Okay, so this is your R, the ideal gas constant. And then what about your little n? The little n is just the number of particles, but now measured in these bundles of moles. It's how many bundles of Avogadro's number of particles do you have? And so it's the capital N divided by Na, and that's just going to equal the number of moles. And so this N over Na, that becomes your little n, and the NaKb, that becomes your R, and ta-da! You have the ideal gas law. PV is equal to nRT. Okay, and so there you go. And finally, let's not lose sight of the important thing that came out of this, because people knew about PV equals nRT way before there was the derivation from Newton's laws. Okay, so they knew about that. But the nice thing that comes out of the Newton law derivation of PV equals nRT is you make this connection between temperature and average kinetic energy of the particles. I mean, that's the amazing thing here. Okay, connecting the microscopics to the macroscopics. And here I did not make the typo that I did above. Okay, the average kinetic energy of the particles in a gas is going to equal 3/2 K Boltzmann times T. Okay, and this is just kinetic energy. All right, and so you can set that equal to 1/2 mv squared. And you know what that means? Given the temperature of a gas, you're going to be able to figure out how fast the particles are moving. Okay, we'll do a problem like that in a minute. All right, now I did sweep some details under the rug, and I don't want to overly complicate this because I kind of want to focus on the general theory here, but this is really only true for monoatomic gases. And monoatomic gases are gases where, you know, they're made up of just atoms. Helium is an example of a monatomic gas. Neon is an example of a monatomic gas, and so on. All right. In reality, you also have diatomic gases, and for diatomic gases, it's actually 5/2 K Boltzmann times T. Okay, so not to confuse things, but you know, I didn't want to be inaccurate in giving you this lecture and saying that it's always 3/2 K Boltzmann T. No, it's sometimes 5/2, and you go, why is it 5/2? Sometimes for diatomic and 3/2 for monatomic, and the answer is because what does an oxygen molecule look like? So diatomic means a molecule that's made up of two atoms. Okay, you say, well, what does it look like? Well, what it looks like is a dumbbell. Like, you know, so here's one oxygen atom, here's another oxygen atom, they're stuck together, and they kind of tumble around one another. So guess what? Not only do they have translational kinetic energy, but they also have rotational kinetic energy. And so the translational kinetic energy part gives you the 3/2, and the rotational part gives you another 2/2 for a total of 5/2 K Boltzmann times T. Okay, so you know, I don't want to go too deep into this, and then it gets even more complicated, because what happens is that even diatomic gases will give you 3/2 at low temperatures, because you have to get above a certain temperature before you start to activate that rotational motion. And so yeah, you know, let's not go down that path. Okay, but you know, again, in the name of accuracy, I didn't want to just leave you with this 3/2 K Boltzmann times T without telling you, yeah, there's more to the story than what I just gave you. Okay, and the problems that we're going to work on, we're just gonna work with 3/2 K Boltzmann times T. Okay, so well, there you go. Now let's return, before we actually do problems here, let's return to the question of why ideal gases actually make these perfect thermometers. Okay, so you know, like, we have all the machinery now to really understand why, when we plotted V versus the temperature for these ideal gases, they really did extrapolate down to uh, absolute zero. Okay, so here's how you would do this experiment. They're not easy experiments to do, but they can be done. Okay, so what you do is you have a piston. Okay, you can imagine it like a beaker, which is just open on the top here. Okay, so this is a possible area where it's open, and you trap some gas in there and you put a piston in there. Okay, now the piston inside of the cylinder, the piston can move freely up and down. Okay, and to make matters even worse, you have to imagine that it can move up and down frictionlessly. So there, you know, the walls here, they have to be tight enough that they don't let the gas out, but there has to be no friction. So you can see how, you know, this is a tricky experiment to do. Okay, now out here, I didn't say it's a vacuum, but you can imagine there's a vacuum outside of the cylinder. Now, if you had a gas with some pressure inside, and there's no pressure outside because it's a vacuum, poof, it would just pop the lid right off of this thing and the gas would escape. But what we're going to do is we're going to put a mass M on the top of the piston to hold it down. Okay, and now we know exactly how much pressure is being applied to that gas, the pressure of the gas. Why? Well, because this is a mass M, okay, and it has a weight mg. So that weight mg here is pushing down on the piston, and the piston has an area A. So if you have a force mg over an area A, a force divided by an area, there's your pressure. Okay, so we know exactly how much pressure is being applied to the gas, and that's the pressure of the gas. Okay, that's the internal pressure of the gas. All right, again, you know the force, mg, you know the area, A, force divided by area, pressure. Okay, great. So the pressure in this experiment is not going to change. I'm never going to take that M off of the piston. All right, what I'm going to do instead is I'm either going to heat the gas or cool it. Okay, so right here, that picture there is a sorry excuse for a Bunsen burner with a flame. Okay, so you can imagine me adding heat to the gas, or you can imagine me putting this in contact with something cold and taking heat out of the gas. Okay, and what happens is, of course, when you remove energy or you add energy, the energy goes somewhere. It goes into the energy of the kinetic energy of the particles. Okay. Now imagine that the particles, they're smacking up against that piston. The piston, if there were no molecules smacking into it, it would just fall, right? Because gravity's pulling it down. What's stopping it from falling? Well, it falls, but then a molecule comes up and boink, and it pushes it back up. Boink, boink. And it's not just one, because one molecule striking the piston is really not going to do anything. It's a whole bunch of them. It's like 10 to the 23 of them. And so they're just boink, 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 boink. And the piston wants to fall, but the pressure of the molecules hitting the piston keeps pushing it up. And guess what? It reaches an equilibrium height. Okay? So the piston wants to come down. The molecules want to push it up. All right. Now, why does it reach an equilibrium height? So you can imagine what happens if this drops too far. It's not that the particles speed up or slow down. They're going to have the same average kinetic energy. But because the volume is smaller, there's more of them. And so they're going to be hitting faster, and that'll tend to push the piston up. However, if the volume gets too big, then there's not enough of them hitting it, and then the piston starts to fall down. At some point, there's this perfect balance between how many and how hard the particles are hitting the piston and how much the piston is exerting a force down. Okay, and when the two get balanced, you reach an equilibrium volume. All right, now what? Well, suppose I start to cool this off. Well, if I cool it off, the molecules are not going to have quite as much oomph, and the piston will start to fall until such time as it reaches, it compensates so that, yeah, the molecules are hitting with less force, but they're hitting more often because the volume is smaller, so there's the greater density of them, they hit more often. So let me keep that up. Let me just keep cooling it down, cooling it down, cooling it down. Well, eventually you get to the point where, you know what, it doesn't matter how much the volume shrinks, because each of the particles, they just have no oomph at all. They got no kinetic energy at all. So they're not going to hold this thing up at all. So what happens at that point is the volume just shrinks down to zero. Again, it doesn't actually shrink to zero because the particles themselves, atoms or molecules, they have some volume associated with them. But you know what? They're all squished together into like a solid. Okay? And so what you could see here, that at absolute zero, all the particles have just dropped to the bottom. The volume is vanishingly small, and the mass has just squished them all down. Okay, squish them all down like that. So now we have a different picture of what absolute zero is. Absolute zero is the temperature at which motion stops. Okay, if these particles are at absolute zero, their average kinetic energy is 0 joules. Okay, they've got no kinetic energy. What's kinetic energy? 1/2 mv squared. They still have a mass, but if they have no kinetic energy, they have no velocity. So at absolute zero, the particles are just not moving at all. They have no velocity. And that is another way to think about absolute zero. Absolute zero is the temperature at which motion stops. Okay, and there's no velocity at all. Another way to understand that there's no such thing as a negative temperature is think temperature is kinetic energy. Kinetic energy is always positive. There's no such thing as negative kinetic energy. Okay, mass is positive, V, it doesn't matter if it's positive or negative because you're going to square it. So kinetic energy is always positive. What's the smallest that kinetic energy can be? Zero joules. That's the energy of something that's not moving at all. So if something's not moving, it has zero um, joules of energy. Its velocity is zero. It's got 0 joules of energy. The temperature is zero. Since there is no such thing as slower than stopped, I don't even know what that means. You can't have something which is going slower than zero velocity. You can't have a temperature that is colder than absolute zero. Okay, and so there you go. That's our picture into what temperature is, right down to this magical absolute zero at which all motion stops. All right, now we can do a problem. All right, and these problems are pretty easy. We're going to use PV equals nRT. But the only difficulty with them is what units, okay? And there are lots of different units for measuring things. So you can measure volume in liters, you can measure volume in milliliters, you can measure it in cubic meters or whatever. We need to use cubic meters because that's the MKS unit, okay? And the same thing with atmosphere. You could say, well, the pressure is 3 atmospheres or 7 atmospheres or something like that. But we need to measure our pressure in pascals, okay? And our temperature, we have to use an absolute scale, and we're going to use Kelvin, okay? So the only trick, if you want to say, the only difficulty in these that I've seen students have in the past is basically the conversion of the units to the right units, okay? And so let's jump into the problem. A gas has a volume of 3 liters at a temperature of 30 degrees Celsius and a pressure of 1 atmosphere. Okay, so I give you a situation. Question A is, how many particles make up this gas? All right, we can actually answer that now. All right, and part B is, if we increase the volume to 5 liters and increase the temperature to 120 degrees Celsius, so not only did we let it expand, but we also heated it up, what's the resulting pressure? Okay, so let's answer part A first. And to do that, we have to do this unit conversion. And so let me start off by telling you how you convert between liters and cubic meters. In chemistry, you tend to use liters a lot. So it is worth, knowing this for your connection to other courses, or even in biology. Okay, so 1 cubic meter is basically 1,000 liters. All right. So what does that mean? That means that 3 liters is 0.003 cubic meters. In other words, if you want to convert from liters to cubic meters, just divide by 1,000. Okay, and that's what this is saying right here, that conversion in there. Okay, the 30 degrees Celsius, well, we can't use Celsius. We have to convert to an absolute scale. You just add 273. Okay, because that adjusts where the zero is of the Celsius scale. Okay, so 30 plus 273, and so that means that your temperature actually is 303 Kelvin. Okay, and 1 atmosphere, if you remember, that is 101.2 kilopascals, but you work in kilopascals, or you speak in kilopascals, but you have to convert to pascals, okay? And so that's 1.012 times 10 to the 5 pascals. All right, and to solve the problem, we're going to use this other form of PV equals nRT. That is, PV is equal to N to K Boltzmann times T, okay, to find capital N, which is the number of particles. Rearranging it, okay, we've got N as PV over K Boltzmann T. Plugging in the numbers, crunching it through your calculator, you find that you have, in this gas, 7.26 times 10 to the 22 particles, okay? And again, I'm saying particles because I don't know if they're atoms, like say helium, neon, which are just individual atoms that are flying around, or they could be like a diatomic gas like N2 or O2 or something like that. Okay, but they're just the individual particles that are flying around, smacking into the walls of the container. All right. Now, that answers the question, but just for practice, say I asked you, in addition to that, I said, well, you know what, convert this 7 times 10 to the 22 particles, convert that into moles. How do you do that? You just divide by Avogadro's number, okay? And Avogadro's number is 6.02 times 10 to the 23. If we divide here, we simply get that we have 0.121 moles, okay? So the gas is made up of 0.121 moles. So I think you can see why moles are kind of a more interesting unit, or it's something that people tend to use a lot. No one likes to go around saying 10 to the 23, 10 to the 22, something like that. Rather, you just say moles, and macroscopic number of particles is generally around 1 mole or a tenth of a mole, or somewhere in that range. Okay, and so moles are a more manageable number. They're easier for our heads to get around. All right, now that answers part A, the number of particles. Part B, there's a couple of ways to do it. I'm just going to show you one right now, but there's a couple of ways to do it. And when you have pressures changing and volumes changing and temperatures changing, you can consider that as having like some initial condition, some initial P1 V1 T1 being changed to another state which it has P2 V2 T2. Okay. Now, in that change, even though I didn't say it explicitly in the problem, I think it's pretty obvious that the number of particles is not going to change. We're not going to add gas, and we're not going to take gas away. We're kind of got this gas trapped inside of a cylinder, and we're simply going to change the volume of the gas and the pressure of the gas and the temperature of the gas accordingly. So what you can do is you can rewrite PV equals nRT, or PV is equal to NK Boltzmann T. You could just put the N and the K Boltzmann too, because that's just a constant. You can put that on the left-hand side. What you get on the right-hand side is PV divided by T. Okay. Now that is going to be the same whether you're talking about the initial state, subscript 1, or the final state, subscript 2. And so you can write that K Boltzmann times N is equal to P1 V1 T1, which are the initial pressure, volume, temperature. But that's also got to equal P2 V2 T2 over T2, which is the final pressure, volume, temperature. Okay. Now, why would I want to do this? Why did I go through this business of writing it this way? And at this point, you can actually forget about the K Boltzmann times N. Okay. The whole reason for doing that is to say, well, both of these have to equal that because the number of particles didn't change, and of course, K Boltzmann doesn't change. Okay. So, what was the advantage of doing that? The advantage of writing it this way is that you don't have to worry about converting the units. As long as P1 and P2 are both in the same units, V1 and V2 are in the same units, T1 and T2, well, they have to be still in absolute temperature, Kelvin, but, whether you use Kelvin or some other absolute temperature scale, it'll work, but they still have to be, in an absolute temperature scale. You don't have to convert the units. Mostly it's P and V, okay? P and V are the ones that cause some trouble. And so, you know what? I'm just going to go ahead and use the numbers without having converted them to MKS. And so what you see there is that initially the gas was at a pressure of 1 atmosphere. Initially V1, the volume V1 was 3 liters, and initially the temperature was 303 Kelvin. Okay. Now, it increases to some pressure, which we don't know, that's P2, but the volume, I tell you in the problem, that the volume increased to 5 liters, so I just put 5 liters in there. Don't even bother converting it to MKS. And the temperature afterwards is going to be 120 degrees Celsius, but again, in absolute scale, that's 120 plus 273. Okay, and so you could see that by doing this, you avoided any of this kind of conversion business with P's and V's. Okay, and poof, out it comes. Now, of course, because we were working in atmospheres, the answer for P2 is going to come out in atmospheres, but there it is, 3.89 atmospheres. All right, and so this will save you some time, say on a test, so you don't have to do the conversion or possibly even make a mistake in doing the conversion. All right, so last thing, just to emphasize once again, all of these insist on an absolute temperature scale. Okay, and there's only one absolute temperature scale that I introduced to you, and that's Kelvin, and so T must be in Kelvin, otherwise this would just not work. Okay, now don't lose sight of the fact that temperature is this average kinetic energy. And so I've got another example here where we're actually going to be able to calculate how fast those particles were moving. Okay, so here in this example, I say if the gas in the previous problem is neon, okay, and neon has an atomic weight of 20 AMUs. Now, if you don't know what that is, I'll mention it as I'll discuss that as I solve the problem. But, if we're working with neon with atomic weight 20 AMUs, how much kinetic energy on average does each particle have? Okay, and how fast is each particle going at 120 degrees Celsius? All right, so you don't need the pressure, you don't need the volume, all you need is the temperature. If I tell you the temperature, and I tell you, the mass of any one particle in the gas, then you should immediately be able to tell me the average kinetic energy and the average speed at which the particles are moving around. Okay, so here we're going to use our equation that the average kinetic energy is equal to 3 halves k Boltzmann times T. Okay, and this is true for any atom. All right, and the k Boltzmann, that is 1.38 times 10 to the minus 23, and T, it's 120 degrees Celsius plus the 273 to convert to Kelvin. And just plug that through your calculator and you're going to get 8.14 times 10 to the minus 21 joules. That is tiny, and you'd expect it because, after all, neon is a very tiny atom. Okay, all atoms are very, very tiny. All right. Now, yeah, it's a tiny amount of energy, but the mass is tiny, so the velocity is not going to be so tiny. So the question is, let's now calculate on average how fast these neon atoms are traveling. All right, so to do that, we're just going to use the fact that the average kinetic energy is equal to 1/2 mv squared. All right, and so we want to find v here. And we can do that because we have the average kinetic energy, we just calculated that, and we have the mass, but I didn't give you the mass in kilograms, and we need to convert it to kilograms. I gave you the mass in the usual mass unit that's used in chemistry or nuclear physics, and that is atomic mass units. And atomic mass units is roughly equal to the sum of the number of protons and neutrons in the atom. Okay, the electrons are fluff. Okay, the electrons are about 1/2000th of the mass of a proton. So the protons and the neutrons, they totally overwhelm the mass of the electron. So all you have to do is basically count the number of protons and neutrons in the nucleus, and that gives you the atomic mass unit. I don't want to get into the details of that. Of course, there's more to that story, but there it is. And I'm not going to expect you to know these atomic weights. I'll give them to you on a test. And so neon has an atomic weight of 20 AMU. 1 AMU, AMU stands for atomic mass unit, 1 AMU is 1.66 times 10 to the minus 27 kilograms. Okay, so if you have 20 AMUs, that's 20 times that number, and so it turns out that one neon atom weighs 3.32 times 10 to the minus 26 kilograms. Well, let's just plug that into our equation up here. Before I do, let's rearrange it because it's kind of annoying to plug in the numbers before you rearrange it. So we have the average kinetic energy is equal to 1/2 mv squared. Let's multiply both sides by 2, divide both sides by m, and then take the square root. That'll isolate v. So you get that v is equal to the square root of 2 times the average kinetic energy divided by m. Plug in your numbers, and you get 2 times the average kinetic energy that we calculated above divided by the mass, and work that through on your calculator, and it turns out that it's 700. Since we worked in MKS units, that'll be 700 meters per second. So at 120 degrees Celsius, which is pretty hot, okay, it's hot, certainly hotter than boiling water, okay, at 120 degrees Celsius, neon atoms would be flying around at an average velocity of 700 meters per second. Okay, so there you go. Now, if I increase the temperature over 120, what would happen? The average kinetic energy would increase, and the average velocity would increase. Okay, what if I cooled it down? Well, the average kinetic energy would decrease, and the average velocity would also decrease. Okay, so there you go. So from knowing the temperature, you can actually calculate how fast the underlying atoms or molecules in the gas are moving. All right, that's enough for the ideal gas law. Next topic is internal energy, specific heats, and latent heats. All right, so with internal energy, or with a gas, because every single atom or molecule has a certain amount of energy associated with it, if you were to add up all the energies of all the particles that make up the gas, you would have the total internal energy of that gas. Okay, now we call it internal energy because it's energy that you don't quite see. It's inside the material. All right, and usually we think of energy as like either potential energy. If I lift something up high, it has potential energy because if I let go, it'll drop. Or we think of energy as kinetic energy, just the fact that something is moving around, it has some energy because it's got some velocity, okay? Internal energy is a little harder to get your head around. You say, well, where is that energy? It's inside the material. It is actually the kinetic and potential energies of all the molecules bouncing around in there. But you can't see them because they're so small, okay? And if you were to add it all up, that would be all the energy of all the particles bouncing around inside the material. So if you look around your room, you've got like, all this material around you. I can see my cell phone over there. That cell phone has a lot of energy in it. And you say, well, I don't see it moving. It's just sitting there. It's not up high above something, so it doesn't have potential kinetic energy. Yeah, I know. But all the little particles that make it up have kinetic and potential energy. And so that adds up to a lot of energy in there. Okay. And so, like Lake Erie, it's a cold lake. But that doesn't matter, it's not at absolute zero. So all those water molecules are bouncing around pretty hard. You add up all those energies, there's an awful lot of internal energy in Lake Erie. Okay, and so all materials, just by the mere fact that they're at some temperature, have a certain amount of internal energy. All right. Now, the internal energy of a gas is easy to calculate because if you know the energy for just one particle is 3/2 k Boltzmann times T, and you have n particles, well then the total internal energy, which we'll use the symbol U for, is just going to be the average kinetic energy multiplied by n. Okay, so the total energy of the system will be 3/2 n k Boltzmann times T if you have n particles. All right, basically you're just adding them all the energies up for each of the particles, and that'll add up to n times the average of any one of the particles. All right, I think that's pretty obvious. Okay, so it's an intensive quantity, meaning that the more gas you have, the more internal energy you have. All right, but usually we don't think in terms of like just absolutely how much energy do you have. Generally, we think in terms of adding heat or removing heat from a material. Okay, so the above formula, I can actually change it and I can say, look, the internal energy of the gas would change by delta U if its temperature changes by delta T. Okay, and so this, that if you were to put some material over top of like a Bunsen burner, you're adding heat to it. That heat is the energy. Well, what happens to the material? It gets hotter. The temperature goes up. So as you add heat to the material, you're adding heat, you're putting energy into this internal energy, you're increasing the internal energy. As you increase the internal energy here, if you increase it delta by amount delta U, well then there's going to be a corresponding increase in the temperature delta T. Okay, and this kind of makes sense. The more heat you put into something, the hotter it's going to, the higher the temperature is going to be. All right, and actually you can calculate the rate at which the temperature increases by how much energy you add. All right, for a gas, it's actually 3/2 nk Boltzmann. All right, so the rate at which the temperature increases with added energy is given by this formula here. We're actually not going to use this formula, but we're going to think of this formula as an inspiration for the specific heat, which I'm going to define next. Okay, so the specific heat of a material, and so we're going to go beyond gases now. We concentrated on gases because they gave us perfect thermometers, but really a lot of the stuff that I'm telling you about will go on beyond, or can be applied to things beyond just ideal gases. Okay, and so we're going to just talk about any material, solid, liquid, or gas. Okay, and we're going to talk about its specific heat, and the specific heat is basically defined as how much energy do I have to add to the system, how many joules of energy do I have to add to the system, such that 1 kilogram of the material would heat up by 1 degree Celsius. Okay, so I've got 1 kilogram of this material. I'm going to give some energy to it, or do some work on it, or something. I'm going to get some energy into this. How many joules of energy do I have to add such that that 1 kilogram goes from, say, 20 degrees Celsius to 21 degrees Celsius? Okay, the amount of energy it takes to increase 1 kilogram of the material by 1 degree Celsius, or 1 Kelvin degree because they're the same size, is equal to the specific heat. Okay, and so we get this formula here. All right, so this formula was basically inspired by the previous formula for the ideal gas, but for the ideal gas we didn't have this MC here. okay, we had basically the 3/2 Nk Boltzmann. But both of them are extensive quantities, which is why I mentioned that they're extensive quantities. In other words, the more material you have, the more energy it's going to take to increase it by 1 degree Celsius. Okay, and so intensive just means, the more material, the more uh, energy it takes. Okay, and so here we're going to simply define the specific heat, and it's given the symbol capital C like that. We're going to define the specific heat by this formula. The energy required is going to equal the mass of the material multiplied by the specific heat of the material multiplied by the temperature that you want it to increase by. Okay, so you say, look, I want the temperature to increase by no, I want to increase the increase the temperature by delta T. Well, if I take delta T, I multiply it by the specific heat, and I multiply it by the amount of material, this formula will tell me how much energy I have to put in to get that temperature increase. Okay, so there you go. And specific heat, it's not it's just a quantity that depends on the type of material. All right, and so we can actually rearrange that formula and look at the units. The units of the specific heat are actually delta U. The units of delta U divided by m delta T, and that's equal to joules divided by kilograms degrees Celsius. All right, and there you go. So what are some specific heats? Okay, um, the specific heat of water is 4,186 joules per kilogram degree Celsius. That means to heat up 1 kilogram of water by 1 degree Celsius, it's going to take 4,186 joules. In fact, the person who discovered that was Joule himself. What he did was he had basically this paddle in water, and the paddle would stir the water, so it would just deliver its energy to the water. And once the paddle had actually delivered 4,186 joules of energy to the water, he discovered that the water heated up by 1 degree Celsius. All right. And the other unit, we're not going to use this unit, but the unit that's used in chemistry a lot for energy is 1 calorie. Okay, it's also used in biology for food energy, but that's how the calorie is defined. The calorie is defined through the specific heat of water. Basically, the amount of energy it takes to increase the temperature of 1 gram of water by 1 degree Celsius is 1 calorie of energy. Okay, so I just mentioned it here in passing because you've probably heard of calories in your other courses, but here we have the specific heat of water in joules per kilogram degree Celsius. Now, the phase of the material does matter. Okay, and phase is like whether it's in a solid or a liquid or whatever. And you know that water can become a solid, ice, or water can become a gas, steam. And so if you convert from water to ice or water to steam, the specific heat also changes. So the specific heat of ice turns out to be only 2,150 joules per kilogram degree Celsius, and the specific heat of steam is 2,010 joules per kilogram degrees Celsius. All right, and just for another example, I picked iron. Okay, and it turns out that iron has a specific heat of 460 joules per kilogram degrees Celsius. Okay, and so it's just a property of the material itself. So you tell me the material. It doesn't matter how much of the material is there. It's just a property of that material. Okay, the specific heat. All right, so now we're ready to do some problems with that equation. Okay, and the first one is kind of an unusual problem. I really want to show you that energy and heat are the same thing. I mean, we say heat because we talk about this internal energy, the energy that's kind of hidden away in the motion of all the molecules inside the material. All right, but it really is just energy. And so last semester, we talked about energy and we said, geez, there's this thing called friction and it seems to mess up our conservation of energy. So where's that energy going? And you've got a car that's moving and the driver hits the brakes and the car comes to a halt. Well, it was moving and it had kinetic energy. Now it's not moving and it doesn't have kinetic energy. Where did that energy go? The car didn't go uphill, so it didn't go into potential energy. Where did the energy go? It actually went into heat, and now we can trace it down. So that's what this problem is meant to illustrate. So we have a car traveling at 100 kilometers per hour, and it comes to a halt. If the car has 4 brakes made up of iron, and each brake weighs 10 kilograms, how much do the brakes heat up by in bringing the car to a halt? In other words, how much does the temperature increase? Okay, and let's assume that the car has a mass of about 1,000 kilograms. All right, and so, well, first thing is, where did that energy go, or how much energy was lost there? And so we say lost in quotes because it's not lost now. We know where it is. It's in the heat. Okay, and so, well, let's calculate the kinetic energy when the car is moving. It's 1/2 mv squared, so that's 1/2 times the mass of the car, which is 1,000 kilograms, multiplied by the velocity, and the velocity was 100 kilometers per hour, but we have to convert that to meters per second. We've done that a lot of times, so I didn't bother you with the details. It's 27.8 meters per second. Okay, and so you just calculate, crunch that through your calculator, and you get 386,420 joules, or 386 kilojoules, which is a significant amount of energy. Okay, so kilojoule is pretty big energy. All right, all of this energy is going to become heat. Why? Well, because the car is moving and it has that energy, and the car comes to a halt, so that energy drops to zero, and that kinetic energy drops to zero, so it went into heat. All right, and that's our delta U. Okay, so now we can go ahead and use delta U is equal to mc delta T. All right. Now we're solving for delta T because I want to know how much the temperature increased for the brakes. And so I'm going to just isolate that first. I'm going to say delta T is equal to delta U divided by mc. What's the delta U? Well, how much energy did we put into these brakes? We just calculated that, 386,420 joules. And what's the mass? Well, one brake is 10 kilograms, but you've got 4 of them, so the total amount of mass that absorbs heat is 40 kilograms. That's where that 40 came from. Okay, and finally, the C, we have to pick the correct specific heat. It's the specific heat for iron, and that's 460. You crunch that through, and that tells you that the temperature has to go up by 21 degrees Celsius. That kind of makes sense, okay? So, that's not the final temperature of the brakes, so don't confuse that. That's how much the temperature went up. So suppose the brakes start off at 20 degrees Celsius, which is room temperature, and you come to a halt, the brakes will actually heat up by 21, and so they'll reach 41 degrees Celsius, okay? So once the brakes heat up to 41 degrees Celsius, the energy's all been absorbed. And I don't recommend you do this because, brakes can get pretty hot. But, if you were to go out there as soon as you stop and you touch the brakes, you would certainly feel that they've heated up. Okay, they heat up. Not so much that, you would hurt yourself, but, you might. I don't know. It depends how fast you're going. But, in this particular case, 41 degrees Celsius, that would be definitely a noticeable temperature increase. All right, so there's one use of the formula. Here's a different one. Okay, this is kind of interesting. Suppose that we have 250 grams of ethanol, okay? And we heat that ethanol up to 60 degrees Celsius. So we've got, say, like a beaker with 250 grams of ethanol heated up to 60 degrees Celsius. And we take that and we pour that into water, 100 grams of water, that's at 20 degrees Celsius. Well, the mixture, the liquids will mix, and they'll come to some resulting temperature, some final temperature. The final temperature will be lower than the 60, but higher than the 20. So what is that temperature? Let's find it, okay? And the only other thing you really need for this problem is the specific heat of the water and the ethanol. I gave you the specific heat of water above. Here's the specific heat of ethanol, okay? You could just look it up. And again, on a test or something like that, I give you these numbers. I don't expect you to memorize them. Specific heat of ethanol is 2,400 joules per kilogram degree Celsius, okay? Now, how does this work? How do you solve this problem? Well, basically what you need to do is realize that energy is conserved. In fact, we're going to see that in a minute. That's the first law of thermodynamics. Energy doesn't disappear. Okay, if you trace it down, no matter where it goes, if it goes into heat, into kinetic energy, into potential energy, we trace it down, you'll always find all the energy there. Okay, so basically, since the ethanol is cooling down as they mix, the ethanol is losing heat. It's losing energy. The water, conversely, is gaining the heat that the ethanol loses, and that process continues until the ethanol and the water are at the same temperature. Okay, and so we can calculate the heat lost by the ethanol, because the heat lost by the ethanol, so I didn't write it as delta U here, but that's the delta U. That's just going to be the mass of the ethanol times the specific heat of the ethanol multiplied by the temperature change of the ethanol. Okay, So we know some of these things. We don't know all of it. We know that we have 250 grams of ethanol, so that's 0.25 kilograms of ethanol. We know the specific heat, 2,400 joules per kilogram degree Celsius. But what's the temperature change? Well, I don't really know, but I know part of it. I know that it starts at 60 degrees and it drops to some final temperature that I'm going to call TF. And so the temperature change will be 60 minus the lower temperature TF. And TF is what we want to solve for. Okay? And so there it is. Okay? So we can't solve this yet for TF because we don't know how much heat was lost by the ethanol. But at least we've got it down to where there's just one unknown on the right-hand side, and that's that final temperature. Once again, what's that delta T? That's like how much the ethanol cools down. It starts at 60. Okay? It ends at TF. And so 60 minus TF is the temperature change, okay? And then all I did afterwards is I just, or below here, is I just simplified this, okay? Now, that's the story with the ethanol. What's the story with the water? So with the water, it's the same thing. But now it's the heat gained by the water. The heat gained by the water is just going to be MC delta T, all for water. Okay. The mass of the water is 100 grams or 0.1 kilograms. The specific heat of the water, 4,186 joules per kilogram degree Celsius. The change of temperature in the water, well, now it's the other way around because TF is a higher temperature and 20 is the lower temperature. So if you take TF minus 20, that tells you the temperature change of the water because the water starts off at 20 degrees and it heats up to TF. So the temperature change is going to be TF minus 20, the other way around for the ethanol. All right. And again, I just simplified that for you. Okay. And now what? Well, energy doesn't just disappear magically. The heat lost is going to be equal to the heat gained. So if I just equate the two, this is the heat lost by the ethanol. Here's the heat gained by the water. Notice that TF is the only unknown. You work it out. Okay, just a little bit of simple algebra there. And you find that the final temperature of the mixture is going to be 43.6 degrees Celsius. Okay, is that what you expected? I mean, always do a little check on you to make sure that the number makes sense. Well, yeah, it has to be less than 60 degrees. I apologize. I noticed that I'm missing a greater than sign. 60 degrees has to be bigger than TF, and the TF has to be between greater than 20. In other words, the final temperature has to be less than 60, greater than 20. It has to be in the middle. And sure enough, it is. It's at 43.6 degrees Celsius. Okay, so well, there you go. There's the story with specific heat. Um, there's another place that heat can go. All right, internally. And this is basically has to do with phase transition. Not every time you add heat to some material does the temperature increase. Okay, so you can have a material, you can add heat to it, and the temperature doesn't change. And you go, when does that happen? Every time, you put water on your stove and you put heat under it in the form of a flame, the water's temperature goes up. So under what conditions can you add heat but the temperature doesn't change? And the answer is when you undergo a phase transition. And a phase transition is basically changing from the solid to the liquid or vice versa, or from the liquid to the gas or vice versa. Okay, and so there's a phase transition. There are lots of phase transitions that's beyond the scope of the course. There's like for instance, remarkably, water has 7 different solid phases. Okay, so even water, even in the solid phase, you can have one solid phase changing to another solid phase, and there's a latent heat associated with that. So, but I don't want to get too far afield with this. Basically, we're only going to consider the 3 typical phases of matter: solid, liquid, gas. Okay, so yeah, you can add heat to something, and if the temperature doesn't change, the phase changes. And so again, back to our stove example, if you have like a pot with a block of ice in it, and you put that on the stove, and you heat it, and you measure the temperature of the water and the ice as it's melting, it stays at 0 degrees Celsius. So you're adding this heat, you're adding this heat, you're adding this heat. The solid is turning into a liquid, but the temperature of the solid, the temperature of the liquid stays constant throughout this transition at 0 degrees Celsius. So, it could take 10 minutes and you're adding heat. 10 minutes worth of heat. Just keep adding heat, adding heat, adding heat. And the temperature doesn't change. What changes is the solid goes to a liquid. Okay? All right. So, well, there you go. And this is known as the latent heat of latent heat. There's two latent heats. There's the latent heat of fusion, and this is for the transition between ice to water. In other words, I should have said here liquid to solid, but we're thinking about water. So whenever you have a transition from the solid to the liquid phase or vice versa, this is known as a latent heat. That's latent meaning heat that you don't see changing the temperature. So there's a latent heat of fusion, the solid liquid transition, but there's also a latent heat of vaporization, and that is the liquid gas transition. All right, and so there's a latent heat associated with that transition too. All right, so what's the formula here? The internal energy changes, okay, during the phase transition, and if you want to actually go from, say, water at 0 degrees Celsius to ice at 0 degrees Celsius or vice versa, how much energy do you have to add or subtract? That's given by this formula. It's M. Obviously, the more stuff you have, the more latent heat you have. It's an extensive quantity. So the more mass you have, the more energy you're going to need. But it's multiplied by this L, which is the symbol for latent heat. Okay. Now, I didn't put a V or an F there because it depends on, this works for both vaporization or fusion, but the numbers are different. So the latent heat of vaporization for water is 2.27 megajoules per kilogram, and the latent heat of fusion for water is 334 kilojoules per kilogram. Okay, notice there's no per degree Celsius because the temperature remains 0 degrees for the fusion and 100 degrees for the vaporization. All right. By the way, this is a remarkably big number. Like steam has just so much energy in it. Even if it's steam at 100 degrees Celsius, it has all this energy. For every kilogram of steam, okay, to get it to steam at 100 degrees Celsius from water at 100 degrees Celsius, you had to add a little over 2 megajoules of energy. Okay, this is why steam engines, were capable of moving locomotives. There's just so much energy in that steam that was capable of pushing pistons, in locomotives back in the Industrial Revolution. All right, so here's a kind of a typical question that one might ask to really get your mind around this. Like, what would be worse if you were burned by water at 100 degrees Celsius or steam at 100 degrees Celsius? Okay, now you might say, oh, well, they're both at 100 degrees Celsius. It's just as bad. One is just as bad as the other. No. Just the fact that they're 100 degrees Celsius, that just says something about the kinetic energy of the particles. But there is much, much more energy in that steam than there is in the water. So being burned by steam is much worse than being burned by water, even if they're both at 100 degrees Celsius. Okay, if you're wondering where that energy is, this latent heat of vaporization, where is it? Well, just think at the microscopic level what's going on. Water has, the molecules, they kind of tumble around one another, but they're close to one another. If you try to pull them apart, they want to pull back together because they're pulled together by electrostatic forces. Okay, and so these water molecules stay kind of close to one another. But to get steam, you have to pull these things apart because in steam the water molecules are each flying off in their own direction without touching one another. And so what you have here is basically the energy. That latent heat is the energy to pull these molecules apart, and there's a lot of energy because between H2O and H2O molecules there's this hydrogen bond, and hydrogen bonds are very, very strong. So this latent heat of vaporization is kind of a measure of that hydrogen bond. So is the latent heat of fusion. Okay, and so that's why water has an extraordinary large latent heat of either vaporization or fusion. Okay, so well, let's do a problem with this. And this problem is actually meant to kind of bring together both the latent heat of fusion and the specific heats. So suppose that we have a 100 gram cube of ice, okay, in the freezer. And freezers generally run at about minus 10 degrees Celsius or something like that. So we got this block of ice, and it weighs 100 grams, and it's at minus 10 degrees Celsius. And what we want to do is we want to heat it up. We want to heat it up, and not only do we want to heat it up to the point where it melts and becomes water, but we also want to get it to the point where that water will then boil, and then the final state is going to be steam, and we're going to keep heating up the steam even after it boils until the steam gets to 120 degrees Celsius. So basically we're starting with ice at minus 10 degrees Celsius, and we're going to add heat until it becomes steam at 120 degrees Celsius. Okay, and so the question is, how much heat does that take for a 100-gram cube of ice? Okay, and part B is it's just kind of like to give you a sense of how long this would take in a microwave oven. Most microwave ovens are like 900 watts. You know, you can actually, when you buy one, you can actually see the ratings. To make the numbers easy, I said our particular microwave oven is rated at 1,000 watts. Okay, so that's the power level. And that means, remember what a watt is from our study of sound? It's joules per second. So that means that this microwave oven is going to give you 1,000 joules of energy every second. Okay, and so how long would it take in this microwave oven to convert this cube of ice at minus 10 degrees Celsius to steam at 120 degrees Celsius? Okay. By the way, don't boil things in the microwave because it tends to be very explosive. All right. Um, as you might have discovered, as I discovered actually just a few days ago when I forgot my tea in the microwave. All right, so actually there are 5 steps to this heating, okay? And so here I am trying to show you the graph. Suppose we take a look at the temperature here, okay? So the temperature is on the vertical axis and the amount of heat that we've added is on the horizontal axis. Heat is sometimes given the symbol Q, like that. All right, and so here are the 5 different phases. First, we start off with ice at negative 10. And we heat that up until we get ice at 0 degrees Celsius. Okay, so that's the first stage in our heating. But then you've got ice at 0 degrees Celsius, and as you add the heat, it goes through a phase transition and it becomes water at 0 degrees Celsius. During that phase transition, what I have here is Roman numeral 2, the temperature doesn't change, and so you can see here that the temperature flatlines at 0 degrees. Great. Now we have water at 0 degrees Celsius. It's all water. What happens now? You keep adding heat, and the water is going to heat up. The temperature is going to raise. You get 20, 40, 80, and then finally gets to 100. Now you have water at 100 degrees Celsius, and you can't go further than that. As you keep adding heat to water at 100 degrees Celsius, the water starts to convert to steam. It undergoes a phase transition. So you have, at this point, water at 100 degrees Celsius, but you keep adding, and then you get steam at 100 degrees Celsius, okay? So now you have steam at 100 degrees Celsius, and you keep adding heat, and now the steam starts to heat up. It's 100 to 110, finally it gets to 120, and you're done. So there's actually 5 steps. You have to calculate 5 different steps for this heating, okay? And I just have them labeled here. It's exactly what I just said, all right? So stages 1, 3, and 5, they're just the regular heating process with specific heat. But stage 2 and 4 in the diagram, those are your phase transitions. 2 is the where the melting, okay, and you'll use the latent heat of fusion for that one. And number 4 is the boiling, and you'll use the latent heat of vaporization for that. All right, so let's do the calculation. So you just have to be careful to use the right formula at the right time. So for stage 1, it's just regular heating, so you use MC delta T, but this time it's ice. Okay, and so yeah, all of them will have 100 grams or 0.1 kilograms, but the specific heat, you got to be careful, it's ice. And ice has a different specific heat than water or steam. So I gave you that above, and I just put the number there. The specific heat of ice is 2,150 joules per kilogram degree Celsius. Okay, and how much are you heating up the ice? Well, you started at minus 10 degrees Celsius, and you got to 0, so you heated up the ice by 10 degrees Celsius. Okay, and so just crunch that too, and it turns out that that part takes 2,150 joules. All right, now where are we at? Now we have ice at 0 degrees Celsius, and we want to turn it to water at 0 degrees Celsius. That's a phase transition. So you use the mass times the latent heat of fusion. The mass, well, that's going to stay the same throughout the problem. It's 0.1 kilograms. Latent heat of fusion, above, I gave it to you. It's 334 kilojoules per kilogram, and that works out to 33.4 kilojoules or 33,400 joules. All right. During the third stage, this is just water heating up from 0 to 100, so you use the specific heat formula. And just be careful, specific heat of water, that's 4,186. The temperature change, well, you start at 0, you go up to 100, so the temperature change is 100. Multiply that through, and you get 41,860 joules for that stage. Okay. Now we're at water at 100 degrees Celsius. Let's boil it. That's going to be a phase transition, so it's MLV, latent heat of vaporization, 0.1 kilograms, and this huge number, 2.257 megajoules per kilogram. That turns out that that particular stage is going to need 225,700 joules. Okay, this is by far the biggest requirement of energy. Okay, isn't boiling it. All right, and then we're still not done because now you want to heat up the steam from 100 to 120. So you have 0.1 kilograms of steam. Specific heat of steam is 2010, and the temperature change is 20 degrees because you're going from 100 to 120, and that's going to require 4,020 joules. Okay, so add them all up, and you get your total. Your total is 307,130 joules, or 307, rounding off 307 kilojoules. Okay, so that's how much energy it would take, 307 kilojoules of energy, to get that ice from negative 10 degrees Celsius to steam at 120. All right, now that answers part A. Part B is, how long would it take a microwave oven to do this? Well, a microwave oven is delivering 1,000 watts of power, so that's 1,000 joules every second. But 1,000 joules, you could just think of that as 1 kilojoule a second. So your microwave oven is actually, it's pretty powerful. It's actually giving the material 1 kilojoule per second. Now, how many kilojoules are you going to need? You're going to need 307 kilojoules. And so this is going to take 307 seconds, okay? Roughly 5 minutes, okay? So with 5 minutes of zapping, you will have this melted and finally turned into steam. Okay, now that sounds about right. That sounds about right. You know that if you've ever heated up like tea in your microwave oven to the point where it's just boiling, you know, that might take up to 3 minutes or maybe 4 minutes. But you know, like a cup is actually 250 milliliters of water, which is 250 grams of water. Okay, and so we've got, you know, significantly less than a cup here. We got less than half a cup of water here in ice form, and so yeah, you know, 5 minutes it'll do it. Okay, so well, there you go. Okay, so that is a story of specific heats and latent heats of fusion. Again, you know, as you add energy to a material, two things can happen. Either the temperature can go up if you're not near a phase transition, or if you are at a phase transition, adding heat, adding energy to it, will convert it from one phase into the other phase. All right, guys, one last topic in thermodynamics, in our study of heat, and that's the second law of thermodynamics. Okay, so let's start off. The second law of thermodynamics is something in addition to the first law of thermodynamics, which is insufficient to describe thermodynamic processes, that is, processes where heat is transferred. So what is the first law? Well, implicitly we've been using it all along, we just didn't name it as such. But the first law of thermodynamics is energy is always conserved. Energy is conserved during any process. Okay, you just have to trace it down. Okay, so if it looks like it's lost, then you missed it somewhere. Okay, look to the heat, because that's probably where you lost it. All right, so you know, great, there it is. But that law by itself is not sufficient to describe all thermodynamic processes. And so let me give you two situations which would actually conserve energy if they did occur. They don't. If they did occur, they would conserve energy, but they never happened. They never happen in nature, okay? And so you're wondering, well, why do these things never happen in nature? If it's conserved, why can't, if energy is conserved, why can't it happen, you know? Like, as long as the law permits it, it should be able to happen. But no, there's a second law of thermodynamics, which says that certain types of processes, even if they would conserve energy, will never happen, okay? So let's take a look at two such processes, all right? So let me scroll down a bit more. There we go. Here's one. Suppose that we have a hot object and a cold object, and we bring them together. Okay, so our before picture has a hot object in contact with a cold object. Well, you know what's going to happen over time. Heat is going to flow from the hot object to the cold object, and that's going to continue. The heat's going to keep leaving the hot object and going to the cold object until both objects reach the same temperature and they're both warm. In fact, we made use of that fact when we mixed the ethanol with the water above and found that, the final temperature was like 43 degrees Celsius. Okay, so as soon as the two reach the same temperature, the heat stops flowing. Okay, so there's a clear before picture and a clear after picture. Now imagine that you made a movie of this and you reverse the time, so you run the movie backwards. What would you see in this movie? Well, what you would see is two materials here. They're both at the same temperature. But for some mysterious reason, one material starts to get hotter and the other material starts to get colder as the heat flows from the one warm material to the other warm material. That just doesn't happen. You never get that heat will spontaneously start flowing from one material to another, heating up one material and cooling down the other. Okay? So here I have before and after. So if you reverse the two, that just doesn't happen. You never get into the situation where your initial condition will be both materials are at the same temperature, and your final condition is where one material is hotter than and the other one is colder. Okay? So that doesn't happen. Does it conserve? If it did happen, would it have conserved energy? Yeah, sure. Because the material that becomes colder, say it loses 100 joules of energy, well, that 100 joules of energy that left the colder material goes into the hotter material, and it increases it by 100 joules of energy. So one's losing 100 joules, the other one's gaining 100 joules. No problem as far as conservation of energy, but it just never happens in reality. So there's something else going on here. It's more than just conservation of energy. Okay, so there's one of the two possibilities. Here is the other possibility. This one's a little harder to see, but nonetheless, it's also a condition. Suppose that you have a mass m, and it's at some height h above the ground, and we release that mass, and it falls down, and it hits the ground. Now, the mass initially had potential energy mgh. When it hits the ground, it might bounce a few times, but then eventually it'll come to a halt. And what happened was the heat, so the energy in potential energy becomes heat in the ground. So initially the energy is in the potential energy of the mass at some height, and the ground is cold. Once the mass falls and hits the ground, it delivers all its energy into the ground, and the ground heats up. Okay, so you have a before picture where energy is potential energy in this mass at a height h, and the ground is cold, and you have an after picture where the mass has fallen and it no longer has its potential energy, but now the ground is hotter. Okay, now the reason this is a little harder to see is because you don't really go around touching the ground after something falls and saying, oh, it's hotter. And even if you did, the amount of heat, the amount of temperature increase is so small that it wouldn't be detectable. Okay, so you go, well, does this really happen? Okay, does mechanical energy, this energy of like the mass falling, does it really become heat? And I mean, the only example that I can think of that you could do is like when you hammer in a nail. So I don't know if you've ever done this, but when you hammer in a nail, you usually use your fingers and you hold the nail in place, and you've got the hammer here, and you smack it so that the nail will go in, and you do this carefully so you don't hit your fingers. But everyone's nailed something in, and try nailing something in that's hard to nail in. You got to really smack it hard. Now, what happens is you touch the nail when you first put it there, and the nail is at room temperature, 20 degrees Celsius. But as you keep smacking it with a hammer, you discover that the nail, it gets warmer and warmer and warmer. And it can get significantly warmer. Then you notice it and you go, well, what's going on? What's causing this nail to get hotter? And the answer is the energy from the hammer strikes is going into the nail, and it's becoming heat. Okay, so this is exactly what I'm indicating up here with this, except that this is not a common everyday experience because we just can't detect these small changes in temperature and so on. But if you had a really, really heavy mass here, and it fell on something, and you measure the temperature before and after, yeah, you would see that the temperature increased. The temperature increased. Now, here's the thing. What if I ran this backwards? What if I make my after picture my before picture, and my before picture my after picture? So I take a movie of this thing falling, and it falls, and then it stopped there. And then I run my movie backwards, and what I would see is here's this thing on the ground, and then all of a sudden, zoop, it pops up into the air. And you go, well, wait, how did that happen? Like, where did the energy to push this mass up into the air? Where did that energy come from? And the answer is the energy came from the heat in the ground. All right? So the heat in the ground will go into this mass and cause it to pop up into the air. Energy is conserved. So it's not that it's a violation. Running this thing backwards doesn't violate the first law. But it never happens. You never see this happening. In fact, when you run a movie backwards, okay, you can tell that things are happening wrong precisely because you'll see situations like this. Things that fell will suddenly pop up into the air. Okay, and you go, wow, that just doesn't happen, so obviously this movie is being run backwards. And then you go, well, maybe it's because energy is not conserved. But no, even running the movie backwards, energy is conserved, because the energy to cause this thing to fly up into the air, that energy came from the ground. So the ground maybe gave it 100 joules of energy. All of a sudden the ground gets cooler by 100 joules, and that energy goes into this mass, and whoop, it flies up into the air. And you go, okay, well, energy is conserved, but this just never happens. It just never happens, okay? So guess what? The first law of thermodynamics is not sufficient. We have to go to the second law of thermodynamics, okay? So what is the second law of thermodynamics? Okay, it actually has two different formulations. And I'm not going to prove that the two formulations are actually identical to one another. But they are, and I'm going to give you both of them because they're both intuitively useful. All right. So the second law of thermodynamics says that no cyclical process exists that has the only effect of either converting all of your heat to work or having heat flow from a cold area to a hot area. Okay. Now, if you think about those two statements, they correspond to the two situations that I just illustrated for you. Okay. So the second law of thermodynamics basically says, no, that can't happen. That just can't happen. Now, this business of a cyclical process, I wanted to give you a proper statement of the second law. And the cyclical process means something that's just going to continue over time. The second law is usually applied to engines, and engines have cycles associated with them. And so, like you have an engine in a car is a four-stroke, four-cycle, four-stroke. There are four phases to the to one cycle in an engine in a car. Okay, so anyhow, in any cyclical process, you just can't have this happening. Okay, so why, and what are the implications of this? So first of all, the why has to do with something in the microscopics, which I'll describe later. I'll try to give you a sense of why the second law of thermodynamics arises from the microscopics. But the other thing we should note about the second law of thermodynamics is that it's often called time zero. Okay, or sometimes called the law of entropy. Okay, things go from order to disorder and never vice versa. All right, and so whenever you see things, and they violate the second law of thermodynamics, you know that someone has reversed time on you. All right, Newton's second law don't care about time reversal. So just to show you that the second law is kind of special, the second law says, no, I can tell forwards time from backwards time. Newton's laws cannot tell forwards time from backwards time. So Newton's laws are actually reversible in time, and they're still totally valid. And you go, well, how can I see that? Well, so just imagine, you have a wall and you have like a billiard ball that bounces off of the wall like that. Okay, so here it is. It starts up here and boink, and it bounces like that. All right. If you run that movie backwards, boink like that, you can't tell. It obeys Newton's laws whether you run it forwards in times or backwards in times. So you can't tell watching that movie of the billiard ball bouncing off of a wall. You can't tell if that movie's running forwards or if someone's reversed it and is running backwards in time. Newton's laws are totally time reversible, meaning if I take t and I replace it with minus t in Newton's laws, they still are totally valid. Okay, but with the second law of thermodynamics, the time symmetry is broken. Forwards time is the real time. Backwards time is just not. It doesn't happen. It doesn't happen. Okay. Otherwise, you would have things popping up off the ground and all sorts of kind of like things that are cold, things that are hot becoming hotter, while things that are cold becoming colder, and this just doesn't happen. Okay. So let's turn now to the why. Why does this happen? So I can't totally do statistical mechanics for you, but I can kind of give you a sense of what's going on there. And it all has to do with really the statistics of what's happening at the microscopic level. Okay, and so just kind of think of it this way: whenever you see time symmetry broken because of some statistical reason, that's the second law of thermodynamics in action. So imagine that you have like a box and you've got 1,000,000 coins in this box, and all the coins are heads up. Okay, we just went around and we ordered all the coins heads up. Okay, and then we shake the box and the coins fall. and the coins went from an ordered state to a disordered state, where roughly half are heads up and roughly half are heads down. Not exactly, but approximately. Approximately half heads up and half heads down. Okay, and you go, yeah, that's believable. I can see how that would work. But now, what if we take that box and we shake it? So we have a box and they're half heads up, half heads down. We shake it, and they all fall heads up. You go, well, what's the odds of that? Well, the odds of that are astronomically small. Astronomically small. Because the odds of the first coin landing heads up are a half. The odds of the second coin landing heads up are also half. The odds of the two together landing both heads up are a half times a half, which is a quarter. So for every coin, you have to multiply by a half. A half multiplied by itself a million times is 1 over 2 to the power 1 million, which for all intents and purposes is 0. So that's a statistically very, very improbable event. Okay, going from the ordered state with all heads up to roughly half heads up, half heads down, that is possible, statistically probable, but the opposite is not. Okay, and so that's the heart of the second law of thermodynamics. You say, well, how does this coin example apply to like the previous examples, the situations that I showed you? Well, let me just show you here in terms of the mass popping up. So what's the ground made up of? It's made up of all these molecules, and they're just bouncing in all different directions. They got energy. They've got energy, and that energy is being delivered to this mass here. But it's being delivered to that mass in some random way. If by some statistical magic all of the molecules in the ground here all conspire to add up their energy in the same direction, okay? Statistically very improbable, but possible in some very, very marginal possibility space, okay? All these molecules, they all just happen to line up, and they all just happen to be pushing their energy up, pushing their energy up, pushing their energy up. Then all of a sudden, all that energy goes into the box, and boom, all of those molecules, all in cooperation, hit the bottom of the box at the same time and pop the box up into the air. And you go, wow, that's not something you see every day. That's right, it's not something you see every day, because that event, although energetically possible, is statistically extremely improbable, to the point that if you saw it, you'd be totally freaked out. Okay, so there you go. There's this the second law of thermodynamics. All right, now this is kind of qualitative. So where would we make use of any of this? And the answer is in analyzing heat engines. Okay, now heat engines, I don't want you just to think of like an engine in a car, although that is a heat engine. Heat engines are anything, any process, and really any cyclical process, because you want this process to continue over time. Okay, any process by which heat is turned into work. And you go, wait a sec. You just said that can't happen. No. What I said in the second law is that you can't have any cyclical process whose only effect is to turn heat into work. Okay, so something else has got to happen, right? And so this word only is very important here. So in a heat engine, there's stuff going on, but it's happening in such a way that some of the heat is being converted into work. Some of it is not. All right, we'll get to that in just a second. For my other situation, I have these two warm places, and one of the warm places gets cooler and the other warm place gets hotter, and so heat is being forced to go from cold to hot. And you say, well, does that happen in the real world? The answer is yes. That's a refrigerator. So a refrigerator is able to move heat from a cold area to a hot area. But once again, that's not the only thing that's going on. There's something else going on in that process, okay? And in moving the heat from the cold area to the hot area, actually you have to do work, okay? And so we're not going to concentrate that much on the refrigerators. We're going to concentrate on the heat engine. But yeah, they're not really violations of the second law, because the second law says the only effect, or the net effect, has to be to turn heat into work. So if other things are going on, like heat is being lost to some other area, then yeah, you can have a little bit of heat turning into work while the rest of the heat does something else. Okay, so yeah, that word only is it was kind of sneaky there. Okay, so let me give you the simplest example of a heat engine that I can think of. All right, so Uh, I think these things are called glockenspiels. I don't know. I mean, like, I remember seeing them as a kid. Basically, you have a candle. Okay, here, like that. There's a candle and there's a flame. Okay, so the flame is a region of hot. All right, and now the air up here is cold, and you know that hot air is less dense than cold air. All right, uh, but the heat in that hot air, it has the energy to displace the cold air as it moves upwards, and so the hot air, it's going to flow upwards into the cold air. Okay, and in that flow, in that convection current, it turns around this pinwheel, and it causes the pinwheel to turn. Okay, so the heat, the flow of the air upwards from hot to cold, will cause a pinwheel to turn. Okay, so is this an example where heat is doing work? Yes, it is an example where heat is doing work. The heat, which is released from the chemical reaction as the wax burns, that heat is turning into the work that is causing the pinwheel to turn. But that's not the only thing that's happening. Yeah, some of the heat turns the pinwheel, but most of the heat actually just rises up into the air, and it heats up the air above. Okay, so it's not, this is not violating the second law, because not all the heat goes into work. Some of the heat goes into work, but some of the heat goes into heating up the air around it. Okay, so you have to have this extra thing. You have to have this heat actually being lost to a cold area in order for some work to be done. Okay, now quantifying that, we'll see that in a minute, but in the next thing, let me just give you kind of a schematic of how all heat engines work. By the way, even the human body can be thought of as a heat engine, okay? Because, like, I've got energy inside of me in the form of food energy, all right? And I can turn that food energy into, into mechanical work like this, okay? And so, yeah, there's the work that's being done by the heat inside my body, but also there's heat being lost into the outside air. Every human being, when we're sort of sitting there, we act like little 80-watt light bulbs. Okay, we're losing 80 joules of energy to the atmosphere. All right, so all heat engines have this basic schematic to them. Okay, basically you have to have one region which is hot. Okay, that's a high temperature region. Okay, usually called a high temperature reservoir. Okay, so there's a lot of energy here, and that energy is in a region where the temperature is hot. TH for hot. Okay. Now, in any one cycle of this engine, you absorb a certain amount of energy, QH, okay, in the form of heat. So QH is absorbed from the high energy reservoir, so the high temperature reservoir. Okay. The engine converts some of that into work, but then must lose some of it into a cold or low temperature reservoir, and the amount of energy that is lost to this low temperature reservoir, we'll call that QL. Okay, so QH is the energy absorbed from the high temperature, and QL is the energy lost to the low temperature, and W is the work done. Well, the first law basically tells us that that energy that's absorbed, it goes into two exits, two destinations, and it's conserved. So the energy that's absorbed from the high temperature has to equal the work done plus the energy that's lost to the cold. Okay. All right, so that's basically the first law applied to a heat engine. Now, there's an efficiency to a heat engine, and that efficiency you can define as epsilon here. And it's basically the amount of work that you get divided by how much energy you absorbed. Okay, so 100% efficiency, it's impossible by the second law, but 100% efficiency would say something like, look, I absorbed 100 joules, that's your QH, and I made 100 joules of work. That's your W. 100 divided by 100 is 1, and that would be an efficiency of 1 or 100%. Okay, but that's not going to happen. A more typical situation is you absorb 100 joules and only 10 joules becomes work, and the other 90 joules is lost. Okay, and so if you do 10 divided by 100, that's an efficiency of 0.1. Okay, so your efficiency is a number between 0 and 1, but it's limited by even more. Okay, and that's the second law, which we'll see in a second. Before that, though, let me just show you different ways that you can write this efficiency. This is one way to write it, but because energy is conserved, W can be written as QH minus QL, all divided by QH, and then if you just distribute the QH over the two terms there, the efficiency can also be written as 1 minus QL divided by QH. Okay, and this is the way that it's usually used, but it can be used in these other forms as well. Okay, now I just said a minute ago that you're going to have more uh, you're going to have something that's going to limit that efficiency. And I'm not going to prove this, but a French physicist by the name of Sadi Carnot, he was a lieutenant in Napoleon's army, and he asked himself a question, what is the most efficient a steam engine can be? Okay, what is the efficiency of a steam engine? He wanted to sort of think out how to make steam engines more and more efficient because he could see that energy was being lost. And so he thought about that, and what he said was, well, let me model the piston in the steam engine as an ideal gas, and he actually came up with what's called the Carnot efficiency. And this is the equation for the Carnot efficiency. It looks an awful lot like the previous one, but instead of QL divided by QH, here you have TL divided by TH. So let's not confuse the two. The Q's are how much energy is absorbed, QH is how much energy is absorbed, and QL is how much energy is lost. Okay, here the T's are the temperatures at which these two reservoirs are at. So TH is the temperature of the high temperature reservoir, and TL is the temperature of the low temperature reservoir. Okay, this is known as the Carnot efficiency, and in order for the second law to be satisfied, whatever the efficiency of the engine is, the true efficiency has to always be less than the Carnot efficiency. So the actual efficiency of any engine is always less than the Carnot efficiency. You can get close to the Carnot efficiency, but you can't get past the Carnot efficiency without violating the second law. Now, I'm stating this without any kind of a proof. The proof is not that hard, but I'm not going to go over it. But basically, what Carnot said is, look, let me take an ideal gas and let me make it go through a cycle where it's pumping something, so it's doing work on something by just expanding and contracting. You can imagine, like this is how the wheels on a locomotive are actually turned. There's a piston, a cylinder and a piston. The piston is filled with steam, and as the steam expands, it turns a wheel. Okay, so Carnot thought about this, and Carnot thought about, how can I make this gas expand and do work while adding heat, and then contract the gas back so that I can repeat the cycle, and I have to absorb heat in order to make the gas contract. So by making the gas expand by putting heat into it, and then making the gas contract by taking heat out, he was basically doing exactly this here. So he basically constructed a heat engine using an ideal gas. So he would absorb heat while the gas expanded and did work, and then he would lose heat as he contracted the gas in order to get it back to the same point where he could repeat the cycle. Okay, so that's roughly how he derived his Carnot efficiency. And then in addition to that, he said, well, any efficiency, any actual efficiency for an engine that you're going to build, like a locomotive or a car engine or whatever, that efficiency is always going to be less than than Carnot's ideal efficiency. Otherwise, the second law of thermodynamics is violated. Okay, and so there you go. That's it. And now we're ready to actually do a problem here. Okay, so let's say that we want to run a heat engine. Okay, and we want to run the heat engine between boiling water, which is at 100 degrees Celsius, and ice water, which is 0 degrees Celsius. And so, you say, well, what does this heat engine look like? Well, it doesn't really matter exactly, but basically you can imagine a gas in a cylinder, and the gas in the cylinder, when you put it in the boiling water, it's going to want to expand, and we'll do some work with that. And then in order to contract it and then repeat the cycle, we're going to take the gas that was in contact with the gas in the cylinder, which was contact with the boiling water. We're going to put it with the ice, and then the ice will cool it off, and it'll contract it, and then we'll repeat this. Okay, so as the gas expands, heats and expands, it's absorbing heat from the boiling water. As the gas contracts, it's losing heat to the ice water. Okay, so we're going to do that, and we know that this engine that we're going to build, it's only going to run at 50% the Carnot efficiency. Okay, which is possible because you can always be less but not more. Okay, so what's that efficiency going to be? Okay, well, we'll calculate it. And so the question I ask is, how much heat is lost to the ice in one cycle okay, of the engine, okay, and assume that in one cycle the engine does 100 joules of work. So just to repeat, the engine's going to do 100 joules of work for every cycle, okay, and I want to know how much heat is going to be lost to that ice, okay, during that cycle. Okay, so this is kind of like heat that we lose. We would love to get work out of it, but we can't because the second law simply limits us. Okay, and so let's do that. All right, so the first thing is what have we been given? And so we've been given that the high temperature is 100 degrees Celsius and the low temperature is 0 degrees Celsius. Carnot's formula, okay, TL over TH uh, are in absolute temperatures, okay, so that's the way he derived it, so we have to work in Kelvin. So TH is 100 degrees Celsius, but we got to convert that to Kelvin, so it's 100 plus 273, giving you 373 degrees Kelvin. That's the temperature of the boiling water, the high temperature reservoir. Okay, and then TL, that's 0 degrees Celsius, which is 270 degrees Kelvin, and that is the low temperature reservoir. All right, so the other thing I tell you is that there's 100 joules of work done. Okay, and also that the true efficiency is 50% of the Carnot efficiency. Okay, well, we have enough information to calculate the Carnot efficiency. So epsilon c is equal to 1 minus TL over TH. That's 1 minus 273 divided by 373, and that turns out to be 0.268. Okay, so what that says is that basically, of all the energy that you absorb from the boiling water, at best, 26.8% of it can become work. Okay, what happens to the rest of it? You have to lose it to the environment, or you have to lose it, sorry, in this case, to the cold ice. Okay, so yeah, like not very good. You're losing most of your energy. You're losing about 3/4 of your energy. So you absorb this energy, about only a quarter of it can become work, and the rest of it has to be lost. But it's even worse in this case because engines don't always run at perfect efficiency. Okay, to get them to run at perfect efficiency, they have to run very, very slow, and every point of the cycle has to be reversible. And so, yeah, engines, insofar as there's some irreversibility to the process, they basically don't run at less than the Carnot efficiency. This one is running at 50% Carnot efficiency, so we're going to multiply 0.5 times that 0.268, and that tells us that this engine runs at an efficiency of 0.134. In other words, of all the energy you absorb from the high, only 13.4% of it will actually become work. Okay, so now we know that epsilon is 0.134. Well, the actual efficiency is the work divided by QH. Okay, and so we just plug in 0.134 is equal to the 100 joules per cycle divided by QH, and we can very simply solve for QH. And that tells us that in one cycle of this engine, it will absorb 746 joules from the boiling water. It will lose 646 joules to the ice, and 100 joules of it will actually be doing some kind of work. Okay, and again, that work is done as the piston expands in the gas when it's in contact with the boiling water. Okay, guys, that's the end of our study of thermodynamics.